Welcome to a quiet exploration of distance, time, and the limits that once defined the universe. For more than a century, the speed of light has stood as the ultimate boundary, a rule so fundamental that it shapes what can be seen, what can be reached, and what can ever influence the future. Nothing, according to our deepest physical laws, was meant to move faster. And yet, in recent years, scientists have begun to describe something different, not a way to outrun light, but a way to step around it. Why faster than light was thought impossible. For as long as humans have looked into the sky, speed has felt like freedom. The faster something moves, the farther it can go. The farther it can go, the larger the universe feels. But modern physics placed a firm boundary on this intuition. A boundary not set by technology, but by reality itself. The speed of light is not simply the speed at which light travels. It is the speed at which information moves. It defines how cause and effect connect across space and time. If something were to move faster than light, it wouldn't just arrive early. It would arrive before it left. This is why faster-than-light travel was long considered impossible. When Albert Einstein introduced the theory of special relativity, he revealed that space and time are not separate things. They are woven together into a single structure known as spacetime. Within this structure, the speed of light remains constant for all observers, no matter how fast they themselves are moving. This constancy has consequences. As an object accelerates toward the speed of light, time slows down for it relative to the outside world. Length contracts along the direction of motion. Energy requirements rise sharply. Reaching the speed of light would require infinite energy, an unachievable condition. But the most profound consequence lies deeper. If faster-than-light motion were possible in the usual sense, causality would unravel. Effects precede causes. Signals could arrive before they were sent. The universe would lose its ability to define before and after consistently. Physics does not tolerate this. Causality is not a preference, it is a structural requirement. Without it, prediction collapses. Laws lose meaning. The universe becomes internally inconsistent. For decades, this seemed to close the case. Science fiction imagined warp drives, hyperspace lanes, and instant jumps across the stars. Physics responded with silence. The equations were clear. Motion through space could not exceed light speed without breaking time itself. But this conclusion rested on an assumption that went largely unquestioned. It assumed that travel must mean moving through space. What if that assumption was wrong? What if the universe allows a different kind of motion, one where distance changes, but speed does not? This question did not arise from fantasy. It emerged quietly from cosmology, from observations of the universe itself. When astronomers began measuring the expansion of the cosmos, they noticed something strange. Distant galaxies were moving away from us, not because they were flying through space, but because space itself was expanding between us and them. And some of those galaxies were receding faster than the speed of light. This did not violate relativity, because nothing was moving locally faster than light. Space was simply stretching. This subtle distinction would change everything. Why faster than light was thought impossible. For a long time, the expansion of the universe felt like a distant curiosity, something relevant only to cosmologists mapping galaxies across billions of light years. It did not seem connected to the question of travel, propulsion, or motion. Expansion was something the universe did on its own, far beyond any human scale. But hidden inside that expansion was a quiet contradiction. If the speed of light was truly an absolute limit, How could distant galaxies move away from one another faster than light without breaking the rules of physics? The answer was subtle, and it required letting go of an assumption that had shaped intuition for centuries. Nothing was moving through space faster than light. Space itself was changing. In Einstein's framework, space and time are not passive backgrounds. They are dynamic. They can stretch, curve, and evolve. Objects move within space-time, but space-time itself can also change independently of the objects inside it. This distinction is easy to overlook, but it is crucial. When a galaxy recedes faster than light due to cosmic expansion, no object locally outruns a light beam. Instead, the distance between 2 points increases because the geometry between them expands. Relativity remains intact because the speed limit applies only to motion through space, not to the expansion of space itself. At first, this seemed like a technical loophole with no practical consequences. After all, cosmic expansion is incredibly gentle at human scales. Space expands by tiny fractions over vast distances. It does not tear apart atoms, planets, or even galaxies. Locally, gravity and other forces easily overwhelm it. But the idea lingered. If space can expand faster than light naturally, then the universe already contains a mechanism for superluminal separation. Not motion, but geometry. Not speed, but distance changing over time. The speed limit had not been violated. It had been bypassed. This realization forced physicists to rethink what travel even means. Traditional motion involves accelerating an object through space, increasing its velocity relative to its surroundings. That kind of motion is strictly limited by relativity. But what if travel did not require acceleration? What if an object could remain stationary within its local space-time, while the space-time around it changed? In such a scenario, the object would never locally exceed the speed of light. It would never experience extreme time dilation. It would not require infinite energy, and yet, its separation from distant points could change faster than light would normally allow. This was not a proposal yet. It was a question. Questions like this often sit quietly for years, sometimes decades, before mathematics catches up. In the late 20th century, that mathematics finally began to emerge. Physicists started exploring exact solutions to Einstein's equations. Not approximations, not thought experiments, but precise geometries that space-time itself could, in principle, adopt. These equations do not describe forces in the usual sense. They describe how energy and momentum shape space-time, and how space-time, in turn, guides motion. Most solutions to these equations describe familiar things: black holes, expanding universes, gravitational waves. But the equations are vast, and they do not forbid exotic geometries. They only require consistency. And consistency, it turned out, allowed something unexpected: a configuration of space-time in which a region could move relative to distant space without locally breaking the speed of light. A configuration where space compressed in front of an object and expanded behind it. A configuration where distance changed faster than light could traverse it, even though nothing inside that region ever did. This idea did not emerge from a desire to build starships. It emerged from mathematics. The equations did not say such geometries were easy. They did not say they were practical. They did not even say they were stable. But they did say something important. They did not forbid them. For physics, that distinction matters deeply. What is forbidden is impossible in principle. What is merely difficult remains open. And what remains open can, over time, reshape understanding. The speed of light, once thought to be an unbreakable wall, began to look more like a boundary condition, a rule about local motion, not about the structure of space itself. This reframing did not invalidate relativity, it deepened it. Einstein's theory was never about speed alone. It was about the geometry of reality. The speed of light emerged as a consequence of that geometry, not as an arbitrary cap. And geometry, unlike speed, can be reshaped. This did not mean that faster-than-light travel was suddenly possible. Far from it. The energy requirements appeared extreme. The materials required were unknown. The control of space-time itself seemed well beyond any conceivable technology. But the most important shift had already happened. The universe had not said no. It had said something quieter. It had said, "Not that way." For over a century, the problem of faster-than-light travel had been framed incorrectly. It had been treated as a question of engines, thrust, and velocity. But the universe was pointing toward a different approach, one that did not involve outrunning light, but redefining distance itself. This insight would lead to one of the most surprising ideas in modern theoretical physics. The quiet loophole inside relativity. The idea that space itself could move faster than light feels counterintuitive because everyday experience offers no reference for it. On Earth, space feels fixed and absolute. Objects move within it. Distances feel permanent. Motion seems to be the only way to get from one place to another. But the universe does not share this intuition. At cosmic scales, space is not a static stage. It is an active participant. It stretches, curves, and evolves, carrying galaxies with it without asking them to move at all. This behavior is not an exception to relativity. It is a direct consequence of it. Einstein's equations do not describe gravity as a force pulling objects through space. They describe how energy and mass shape space-time itself, and how that shaped space-time guides motion. In this framework, motion is secondary. Geometry comes first. This is where the quiet loophole appears. Relativity restricts how fast objects can move through space, but it places no such limit on how fast space itself can change. Distance is not a fixed quantity. It is something that can grow, shrink, or warp depending on space-time's geometry. The universe already demonstrates this on the largest scales. Two distant galaxies may be separated by 1 billion light-years today, and by more than 1 billion light-years tomorrow. Not because either galaxy moved, but because the space between them expanded. Over large enough distances, this expansion causes separation to increase faster than light could cross the gap. Nothing breaks. No signal outruns light locally. No causality violation occurs. Each galaxy remains at rest in its own local frame. Relativity remains intact. This distinction between local motion and global separation is subtle, but it changes everything. Local motion is constrained. Global geometry is not. Once physicists recognized this difference, a new question naturally followed. If the universe can expand space faster than light in a uniform, natural way, could space also be reshaped locally in controlled ways? Not accelerated violently, not torn or broken, simply curved. Curvature is the language of general relativity. Every gravitational effect, from falling apples to orbiting planets, is explained as motion through curved space-time. Massive objects do not pull things toward them. They reshape geometry, and other objects follow the paths that geometry creates. If curvature can guide motion, then in principle, geometry itself could become a tool. This is where the idea of a loophole becomes something more than an abstraction. A loophole is not a violation. It is a condition the rules already allow. The universe does not object to space expanding, contracting, or bending. It only objects to objects locally exceeding the speed of light. This suggests a different kind of travel. Instead of pushing a spacecraft faster and faster through space, requiring more and more energy as it approaches light speed, one could imagine holding the spacecraft nearly stationary while reshaping the space around it. In such a scenario, the spacecraft would not be moving quickly at all. Locally, it might be almost at rest. Time aboard the craft would flow normally. No extreme acceleration would be felt. And yet, the distance between the spacecraft and its destination could shrink rapidly. This is not motion in the traditional sense. It is relocation through geometry. At first, this sounds like wordplay, a semantic trick to avoid saying faster than light. But in physics, definitions matter. Motion and distance are not interchangeable. Relativity treats them differently. Velocity is limited. Metric change is not. The metric is the mathematical object that defines distance in space-time. It tells you how far apart 2 points are, how time flows between events, and how paths curve. Changing the metric changes reality's geometry. General relativity allows the metric to change. It changes constantly. Every planet, every star, every galaxy slightly alters the metric around it. Space-time is not rigid. It is flexible, though immensely stiff. Massive energies are required to change it noticeably. This stiffness is why everyday objects cannot manipulate space-time in dramatic ways. But stiffness is not impossibility. It is resistance. And resistance can sometimes be overcome. The realization that geometry could, in principle, be engineered did not come from science fiction. It emerged from the mathematics of relativity itself. Physicists asked a simple question: what kinds of space-time geometries are allowed by the equations? The answer was surprising. The equations are permissive. They allow a wide range of solutions, including ones that look nothing like the universe we observe naturally. As long as energy and momentum behave consistently, space-time can take on exotic forms. Most of these forms are not realized in nature because the conditions required are extreme. But the equations do not forbid them. One such form involves regions of space-time that move relative to distant space while remaining locally calm. Inside these regions, nothing unusual happens. Time flows normally. Objects behave normally. But outside, space-time is distorted in a way that changes distances rapidly. This is the conceptual foundation of faster-than-light travel without breaking relativity. It does not rely on outrunning light. It relies on changing what distance means. This idea took time to mature. For years, it remained an odd mathematical curiosity. Something interesting, but impractical. Something to be explored on paper, not in laboratories. But as computational power increased and theoretical tools improved, physicists began revisiting these ideas with fresh eyes. They were no longer asking, "Can this be built?" They were asking, "Is this truly forbidden?" And the universe continued to answer quietly, "No." The quiet loophole inside relativity. As physicists explored this loophole more carefully, they began to realize that it was not merely a curiosity hidden in the equations. It was a structural feature of space-time itself. The universe was not only permitting this kind of behavior, it was already demonstrating it on the largest scales imaginable. Cosmic expansion is not an edge case. It is the dominant behavior of the universe. Every moment, space stretches slightly. Over small distances, this stretching is imperceptible. Over intergalactic distances, it becomes profound. Entire regions of the universe drift beyond one another's horizons, separated not by motion, but by geometry. Light emitted today from some galaxies will never reach us, not because it is too slow, but because the space between us grows faster than light can cross it. These galaxies are not breaking any rules. They are obeying them perfectly. This realization reframed faster than light travel from a forbidden dream into a problem of scale and control. The universe already allows superluminal separation. It simply does not allow superluminal motion. Once this distinction was fully understood, physicists began asking more refined questions. If space can expand uniformly everywhere, could it be made to expand unevenly? If geometry can change globally, could it be reshaped locally? General relativity does not forbid local curvature changes. It describes them. Every gravitational field is a local modification of space-time. Mountains curve space. Planets curve it more. Stars curve it strongly. Black holes curve it so intensely that even light cannot escape. These are not metaphors. They are geometric facts. Gravity, in this view, is not a force pulling objects inward. It is the consequence of space-time geometry guiding paths. Objects follow the straightest possible routes through curved space-time, and those routes appear to us as attraction. If geometry can guide motion, then altering geometry alters motion without applying force. This is the core insight. Motion through curved space is not the same as motion through flat space. An object can follow a path that brings it closer to a destination without ever accelerating in the usual sense. The path itself does the work. This idea already operates in subtle ways. Satellites orbit Earth by following curved space-time, not by constantly firing engines. They move freely, guided by geometry. Scale changes everything. At planetary scales, curvature is gentle. At stellar scales, it is stronger. At black hole scales, it becomes extreme. But the principle remains the same. Geometry shapes motion. The question was whether geometry could be shaped deliberately, not just passively, by placing mass somewhere and letting space-time respond, but actively, by arranging energy in specific configurations designed to produce desired geometric effects. This is where theory pushed into unfamiliar territory. Einstein's equations link space-time curvature to energy and momentum. In principle, any arrangement of energy creates a corresponding geometry. The challenge lies in the type of energy required. Natural forms of matter produce certain kinds of curvature. They pull inward. They create wells. They slow time. But the geometries needed for space-time-based travel require something more subtle. They require regions where space behaves differently in front of and behind an object. This asymmetry is crucial. Uniform expansion does not move anything relative to its surroundings. But asymmetric expansion can. If space contracts ahead of an object and expands behind it, the object's separation from distant points can change rapidly, even if the object itself remains locally at rest. This is not propulsion. It is displacement through metric manipulation. At first, this sounded dangerously close to violating causality. If distances can change faster than light, could information propagate backward in time? Could paradoxes arise? Physicists examined these concerns carefully. The answer, surprisingly, was no, at least not necessarily. Because the object inside such a space-time configuration never locally exceeds the speed of light, signals within it remain causal. From the object's own frame, nothing unusual occurs. Time flows normally. Cause precedes effect. The superluminal aspect appears only when comparing distant frames. Relativity already allows this. The universe does not maintain a single global now. Simultaneity depends on motion and position. Events that are simultaneous in one frame are not in another. Faster-than-light separation does not automatically imply backward causation. What matters is local causality, and local causality remains intact. This distinction calmed one of the deepest objections to faster-than-light concepts. The problem was never speed itself. It was the threat to cause and effect. Once it became clear that geometry-based displacement could preserve causality, the conceptual barrier weakened. What remained were practical barriers. The energy required to significantly warp spacetime appeared immense. Early calculations suggested negative energy densities far beyond anything known to exist. The required configurations seemed exotic, unstable, and unrealistic. But again, physics made an important distinction. Unrealistic is not impossible. Many things once thought unrealistic later became routine. Nuclear energy, gravitational waves, black holes themselves were once considered mathematical oddities. The universe has a history of allowing what mathematics permits, even if technology lags far behind. This historical pattern encouraged caution, not dismissal. Physicists did not claim that space-time travel was imminent. They did not promise engines or vehicles. They continued doing what science does best, refining models, reducing assumptions, testing consistency. And as they did, something interesting happened. The extreme requirements began to soften. New mathematical approaches suggested that the energy needed might be far less than initially thought. Alternative geometries reduced reliance on exotic matter. Some models suggested that small, localized distortions could achieve significant displacement over time. The idea of traveling many times faster than light, in terms of effective distance covered, began to move from the realm of pure fantasy into that of cautious, theoretical exploration. Not because the universe had changed, but because our understanding of it had deepened. The speed of light was still absolute. Nothing outran it. But the universe had revealed a subtle truth. Distance itself is not absolute. It is shaped by geometry, and geometry, under the right conditions, can change faster than light ever could. This quiet loophole did not overthrow relativity, it fulfilled it. Warping space, instead of moving through it. For centuries, motion has been understood as something objects do within space. A ship crosses an ocean. A planet traces a path around a star. A beam of light travels from one point to another. Distance is treated as fixed, and speed is defined by how quickly something moves across that distance. Within this framework, the speed of light stands as an absolute ceiling, not because it is especially fast in a mechanical sense, but because it is woven into the structure of space-time itself. Yet general relativity quietly suggests a different possibility. One that does not rely on breaking the speed limit, but on questioning what the limit actually applies to. Einstein's equations do not forbid space itself from changing. They describe space and time as dynamic, flexible, and responsive to energy and mass. Space can stretch, compress, curve, and evolve. It can expand faster than light without violating relativity, because nothing is moving through space faster than light is allowed to. The distance itself is changing. This distinction is subtle, but it is everything. When cosmologists observe distant galaxies receding from us faster than the speed of light, no laws are being broken. The galaxies are not racing through space at impossible velocities. Instead, the space between galaxies is expanding. Relativity places limits on motion within space-time, not on the behavior of space-time itself. This loophole, quiet and mathematically consistent, is where the idea of faster-than-light travel begins to take shape, not as reckless motion, but as space-time engineering. Imagine standing still on a flexible surface while the surface itself shifts beneath you. You are not moving relative to the surface at all. Yet your position changes because the surface changes. In general relativity, space is that surface. If it can be reshaped locally, compressed ahead, expanded behind, then an object embedded within it could effectively travel vast distances without ever exceeding the local speed of light. This is not intuition speaking. It is the direct implication of Einstein's field equations. The equations of general relativity do not prescribe how space-time must behave. They describe how space-time responds to energy and momentum. Under extreme or carefully arranged conditions, space-time can do extraordinary things. Black holes are one such example. Regions where space-time curves so steeply that familiar ideas of distance and time break down entirely. The early universe provides another, where space expanded exponentially faster than light during inflation. If space-time can expand, contract, and curve on cosmic scales, then the question becomes unavoidable. Could it be manipulated on local scales? The challenge is not whether space-time can warp. We know it can. The challenge is whether such warping can be shaped, controlled, and sustained in a way that produces motion-like effects without violating causality or local physical laws. This reframing changes the problem entirely. Faster-than-light travel is no longer about outrunning light itself. It becomes about rearranging the geometry of the universe around a traveler. Instead of asking how fast a ship can go, the question becomes how space can be shaped. In everyday experience, space feels rigid and absolute. Distances seem permanent. But relativity reveals this to be an illusion born of weak gravitational fields and slow speeds. In reality, space behaves more like a fabric under tension. Mass tells space how to curve. Energy tells time how to flow. Remove the assumption of rigidity and new possibilities emerge. To understand this shift, it helps to abandon the image of a ship pushing through space like a boat through water. That metaphor quietly imports classical assumptions into a relativistic universe. A better image is a ship carried by the motion of space itself. Like a leaf resting on a flowing current, not paddling, but being transported by the shape of the river. The leaf never exceeds the speed of the water around it. Locally, it obeys every rule. Globally, however, it may move far faster than anything swimming under its own power. In space-time terms, this means a spacecraft could remain nearly stationary relative to its immediate surroundings, while space-time ahead contracts and space-time behind expands. The craft would ride a wave of geometry rather than accelerate through a static background. From the perspective of the ship, nothing unusual happens. Time passes normally. No extreme accelerations are felt. No relativistic mass increase occurs. The local laws of physics remain intact. From the perspective of distant observers, however, the ship appears to cross enormous distances in remarkably short times. This is not science fiction logic. It is a direct extrapolation of known physics. General relativity permits solutions where space-time is manipulated in highly asymmetric ways. Most such solutions are physically unrealistic or unstable, but the equations themselves do not forbid them. They simply demand a price. That price is energy, specifically exotic configurations of energy that behave unlike anything encountered in ordinary matter. Before confronting that cost, it is important to understand why the concept is even allowed at all. Relativity is often misunderstood as a set of prohibitions, but it is more accurately a framework of constraints. It defines what cannot happen locally, not what cannot happen globally. Locally, no object can outrun light. No signal can propagate faster than causality allows. No observer can experience time reversal or infinite energy densities. These rules are absolute. Globally, however, space-time itself can evolve in ways that produce counterintuitive outcomes without violating any local rule. The universe has already demonstrated this once, during its earliest moments. In the first fractions of a second after the Big Bang, the universe underwent a period of rapid inflation. During this phase, space expanded so quickly that regions became separated faster than light could travel between them. Yet no information was transmitted faster than light. No particle exceeded the cosmic speed limit. Space itself did the moving. This historical precedent is crucial. It shows that faster-than-light separation is not speculative. It is something the universe has already done. The challenge is scale and control. Cosmic inflation required enormous energy densities distributed throughout the universe. Replicating such conditions locally seems implausible. But theoretical physics is not constrained by engineering practicality alone. Its role is to explore what the laws permit, not what is currently buildable. When physicists began asking whether space-time warping could be localized, confined to a region around a spacecraft, the problem shifted from cosmology to geometry. Could space-time be sculpted into a configuration that behaves like a moving bubble? Inside this bubble, space would remain relatively flat and calm. Outside it, space would be distorted in a carefully arranged pattern. The bubble itself would not move through space. Instead, space would move around it. This idea does not emerge from speculation alone. It arises from exact solutions to Einstein's equations. Solutions that describe how space-time could behave if the right energy conditions were met. Such solutions are rare, fragile, and deeply unsettling. They require forms of energy that behave oppositely to anything familiar. Energy that does not attract, but repels. Energy that violates classical intuitions about pressure and density. Energy that, in some contexts, appears to be less than nothing. This is where the concept of negative energy enters the story, and with it, the boundary between theoretical permission and physical plausibility. But before addressing those challenges, it is worth lingering on the conceptual shift itself. Warping space instead of moving through it reframes faster-than-light travel as a problem of geometry, not velocity. It removes the need for infinite energy associated with near-light speed acceleration. It avoids time dilation catastrophes. It preserves causality at the local level. Most importantly, it aligns with the deepest insight of relativity, that space and time are not passive stages on which physics plays out, but active participants in the drama. When Einstein first proposed general relativity, he replaced the Newtonian idea of gravity as a force with a geometric description of curved space-time. Objects fall not because they are pulled, but because they follow the natural paths defined by space-time geometry. In this sense, gravity is already a form of space-time manipulation. Massive bodies shape the paths of objects around them by altering the structure of space and time. If gravity can curve space-time unintentionally, then advanced engineering, at least in principle, might curve space-time deliberately. This is the conceptual root of all warp-based travel ideas. They do not seek to defeat relativity, they exploit it. That exploitation, however, comes with profound consequences. Altering space-time geometry is not like bending metal or redirecting fuel. It affects causality, energy conservation, and the global structure of the universe. Even small distortions can produce horizons, instabilities, and regions disconnected from the rest of space-time. Any attempt to engineer such effects must contend with these risks. At this stage, the idea remains safely theoretical. No known technology can generate or control the required space-time distortions. No known material can sustain the necessary energy configurations. The equations permit the outcome, but they offer no instructions for achieving it. And yet, the fact that the equations permit it at all is extraordinary. It means that faster-than-light effects are not banned by the laws of physics. They are merely hidden behind conditions so extreme that they lie far beyond our current reach. This distinction matters. A forbidden phenomenon is one that cannot occur under any circumstances. A permitted but inaccessible phenomenon is one that challenges technology, not theory. Warping space belongs to the latter category. As physics progresses, the boundary between impossible and impractical has shifted many times. Nuclear energy was once inconceivable. Black holes were once mathematical curiosities. Gravitational waves were once dismissed as artifacts of calculation. Each of these ideas emerged from equations long before they emerged in reality. Warp-driven space-time manipulation may follow a similar path, or it may remain permanently beyond reach. At this point, the theory alone cannot decide. What it can do is show that the universe allows more freedom than our everyday intuitions suggest. Space is not a rigid container. Distance is not sacred. Motion is not the only way to travel. Sometimes, the universe moves for you. Warping space. Instead of moving through it. To move from philosophical possibility to mathematical structure, physics requires something precise. Not an analogy, not a metaphor, but a solution. A configuration of space-time that satisfies Einstein's equations exactly, even if the conditions it requires are extreme or unfamiliar. Without such solutions, ideas remain speculative, unable to be tested, criticized, or refined. For decades, the notion of reshaping space for travel existed only as a loose implication of general relativity. Physicists understood that space-time could, in principle, behave in flexible ways. But no one had demonstrated a specific geometry that could produce effective faster-than-light motion while preserving local physical laws. That changed in the mid-1990s, when a young physicist posed an unusual question. Instead of asking whether faster-than-light travel was possible, he asked whether Einstein's equations already allowed something like it. The answer came, not from new physics, but from a different way of arranging what was already known. The key insight was to stop thinking about motion altogether. In general relativity, the motion of an object is determined by the geometry of space-time around it. Objects follow paths called geodesics, natural trajectories that require no force or acceleration. In flat space-time, these paths are straight lines. In curved space-time, they bend. If space-time itself could be shaped into a moving pattern, then an object placed within that pattern would simply follow the geometry, without ever needing to accelerate in the conventional sense. The object would not push against space. It would be carried by it. Mathematically, this required defining a region of space-time, a bubble, within which space remained calm and nearly flat, surrounded by a region where space-time was distorted in a very specific way. Space ahead of the bubble would be compressed. Space behind it would be expanded. The bubble itself would propagate forward, not as a material object, but as a pattern in the geometry of space-time. Inside the bubble, time would flow normally. The occupant would experience no extreme forces, no crushing accelerations, no relativistic distortions. From their perspective, they would be at rest. Outside the bubble, space-time would be doing something extraordinary. This configuration is not intuitive, and it is not something that arises naturally. But it is a valid solution to Einstein's equations. That fact alone reshaped the conversation. The equations of general relativity are notoriously unforgiving. They do not permit arbitrary fantasies. Any proposed space-time must obey strict mathematical constraints. If a geometry satisfies those constraints, it is not science fiction. It is physics. The existence of such a solution demonstrated something profound. Faster-than-light effective travel is not explicitly forbidden by relativity, as long as nothing locally exceeds the speed of light. The bubble does not violate causality inside. No signal within the bubble outruns light. No object accelerates beyond permitted limits. The rules hold locally, even as the global outcome appears to defy them. This distinction between local law and global effect is central to modern theoretical physics. Consider again the expanding universe. Two distant galaxies can separate from one another at an effective speed greater than light, yet neither galaxy violates relativity. The same logic applies here, but on a far smaller and more controlled scale. The bubble is not moving through space. It is a region where space itself is being rearranged. From the outside, the bubble's leading edge approaches distant points faster than light could travel through ordinary space. From the inside, nothing unusual occurs. This dual perspective is unsettling because it challenges deeply ingrained intuitions about motion, speed, and distance. But relativity has always demanded that intuition yield to geometry. The deeper implications emerge when one asks what it takes to create such a space-time configuration. Einstein's equations link geometry to energy and momentum. To bend space-time in a specific way, one must supply a specific distribution of energy. Ordinary matter produces familiar curvature, gravity that attracts, time dilation near massive objects, orbital motion. The space-time bubble requires something stranger. In the regions where space is compressed and expanded, the equations demand energy densities that are negative relative to the vacuum. This does not mean energy simply disappears. It means the local energy density is lower than that of empty space. In classical physics, such a concept would be dismissed immediately. Energy is always positive. Matter has mass. Fields carry energy. There is no room for less than nothing. Quantum physics complicates this picture. In quantum field theory, the vacuum is not empty. It seethes with fluctuations, temporary excitations that appear and vanish according to strict statistical rules. Under certain conditions, these fluctuations can be suppressed, producing regions where the energy density is lower than the surrounding vacuum. These effects are small, fleeting, and difficult to maintain, but they exist. This matters because general relativity does not care why energy behaves a certain way. It responds only to what the energy momentum tensor describes. If negative energy density exists, even briefly, space-time responds accordingly. The bubble solution exploits this loophole. It does not require exotic particles or unknown forces. It requires arranging energy, known energy, in a configuration that violates classical expectations, but not quantum law. At least not in principle. The quantities involved, however, are staggering. Early calculations suggested that the energy required to create such a space-time bubble would exceed the mass energy of entire planets, compressed into a thin shell around the bubble's boundary. Later refinements reduced this estimate, But even optimistic versions remain far beyond any realistic engineering capability. These numbers are not incidental. They reflect the extreme stiffness of space-time at human scales. Space is flexible, but it resists being bent sharply unless immense energy is involved. This resistance is why gravity feels weak. It takes the mass of a planet to produce noticeable curvature. To sculpt space-time deliberately, one must compete with cosmic forces. The bubble geometry also introduces additional complications. The front edge of the bubble forms a horizon, an invisible boundary beyond which signals cannot propagate backward into the bubble. This means that once the bubble is in motion, the occupant cannot control or shut it down from inside. The space-time geometry ahead of the bubble determines its trajectory. This raises unsettling questions about navigation and control. How does one steer a region of space-time if signals cannot reach the boundary that defines it? It also raises questions about causality. While local causality remains intact, global causal structures can become distorted. Certain configurations allow paths through space-time that resemble closed loops in time, scenarios where cause and effect become ambiguous. The existence of such paths does not mean time travel is easy or inevitable, but it signals that space-time manipulation on this level interacts dangerously with the foundations of causality itself. These concerns do not invalidate the solution. They reveal its depth. Any serious attempt to manipulate space-time must confront not only engineering challenges, but conceptual ones. Control, stability, and causal consistency become as important as energy supply. Despite these issues, the mathematical existence of the bubble solution had an immediate and lasting impact. It transformed faster-than-light travel from a forbidden fantasy into a legitimate topic of theoretical research. Physicists could now ask precise questions. How stable is the bubble? Can the energy requirements be reduced? Are there alternative geometries that achieve similar effects? Can quantum effects help or hinder such configurations? These questions led to decades of refinement, critique, and reinterpretation. Some researchers argued that quantum inequalities severely limit the amount and duration of negative energy, potentially ruling out macroscopic bubbles. Others explored modified theories of gravity, where space-time behaves differently under extreme conditions. Still others examined whether naturally occurring phenomena, cosmic strings, vacuum fluctuations, or early universe relics, could approximate the required conditions. What emerged was not a single answer, but a landscape of possibilities. The bubble geometry became a reference point, a proof that relativity does not categorically forbid effective faster-than-light motion. It marked a boundary between what is known to be impossible and what is merely difficult. Importantly, this idea does not suggest that humanity is close to building such a device. It suggests something subtler and more enduring, that the structure of space-time is richer than once believed. Physics often advances by discovering what the laws do not forbid. The impossibility of perpetual motion machines revealed deep principles of thermodynamics. The impossibility of superluminal signals within space-time revealed the causal structure of relativity. The permissibility of space-time warping reveals something else: the flexibility of geometry itself. Whether that flexibility can ever be harnessed remains an open question. What matters for now is that the equations allow it. The universe, as described by general relativity, is not a static arena. It is an active medium, capable of configurations that challenge human intuition while remaining mathematically consistent. Warping space instead of moving through it is not a promise, is a permission. And in physics, permission is the first step toward possibility. The Alcubierre concept, Revisited when the space-time bubble first appeared in the equations, it was not introduced as a proposal for interstellar travel. It was presented as something far quieter and far more unsettling. A demonstration. A proof that Einstein's equations allowed a geometry that behaved in a way most physicists assumed was forbidden. Miguel Alcubierre did not claim to have solved faster-than-light travel. He showed that general relativity itself contained a solution where effective superluminal motion emerged without violating its most sacred rule: that nothing locally outruns light. The distinction mattered, and still does. At the heart of the Alcubierre concept lies a precise mathematical construction. It begins by choosing a space-time metric, a way of measuring distances and times, that describes a compact region of nearly flat space surrounded by a shell of intense curvature. This region is not an object in the conventional sense. It is a configuration, a pattern written into space-time itself. Inside the bubble, space-time resembles the calm geometry of deep interstellar space. Clocks tick normally. Distances behave as expected. An observer inside feels no acceleration and experiences no gravitational forces beyond what is intentionally engineered. Outside the bubble, space-time is distorted in a highly asymmetric way. In front of the bubble, space is compressed. Behind it, space is expanded. The asymmetry is not incidental. It is essential. Without it, the geometry would not propagate. The bubble's motion is not defined by velocity in the classical sense. It is defined by how quickly the space-time distortion translates across the background universe. The bubble does not push against anything. It does not exchange momentum with surrounding space. It simply exists as a moving region of altered geometry. This is one of the most counterintuitive aspects of the concept. The bubble's speed is not limited by the speed of light because it is not a physical object traveling through space-time. It is space-time. Einstein's equations permit this because they are local equations. They constrain how energy, momentum, and curvature interact at each point. They do not impose a global speed limit on the evolution of geometry itself. This subtlety is often overlooked, even by those familiar with relativity. The speed of light is not a universal cap on change. It is a cap on how quickly influences propagate through space-time. Geometry changing does not, by itself, transmit information in the same way. The Alcubierre solution exploits this distinction precisely. To make the idea concrete, Alcubierre defined a function that describes how space-time distortion is distributed around the bubble. This function determines the thickness of the shell, the sharpness of the curvature, and the intensity of the energy required. By adjusting it, one can make the bubble smoother or more abrupt, wider or narrower. The equations respond accordingly. Sharper transitions demand greater energy densities. Smoother transitions reduce some requirements, but expand the affected region. There is no free configuration. Every choice imposes costs elsewhere. What the solution reveals is not an optimal design, but a family of possibilities. It opens a space of exploration rather than closing it. One of the most striking features of the Alcubierre metric is the absence of traditional acceleration. In classical travel, reaching high speeds requires enormous forces, which impose severe stresses on both vehicles and occupants. In relativistic travel, approaching the speed of light demands infinite energy. The bubble avoids this entirely. An observer inside follows a geodesic, a natural path through space-time that requires no force. From their perspective, they are inertial. The universe moves around them. This resolves one of the most severe objections to near-light speed travel: survivability. There are no crushing accelerations, no lethal g-forces, no relativistic mass increase. The ship does not become harder to accelerate as its effective speed increases, because it is not accelerating at all. Time dilation also behaves differently. Since the ship is locally at rest relative to its immediate spacetime, clocks inside tick normally. The extreme time discrepancies associated with relativistic flight do not appear in the same way. This does not mean time behaves trivially. The global structure of spacetime still introduces complex, temporal relationships between departure and arrival. But the familiar paradoxes of relativistic rocketry are not the dominant issue here. Instead, new paradoxes emerge. The front of the bubble creates a causal horizon. Signals from inside the bubble cannot reach the region of space-time that determines the bubble's future motion. This means that once the bubble is established and moving, it cannot be controlled from within. Navigation becomes a pre-programmed affair. The geometry must be set in advance. Any error in trajectory cannot be corrected mid-flight. This feature is not an engineering flaw. It is a direct consequence of the space-time structure itself. The bubble's leading edge lies outside the causal influence of the interior. This raises deeper questions about agency and control. Who, or what, is steering a region of space-time once it is in motion? How does one safely start or stop such a configuration? These questions have no simple answers. Another consequence is the presence of extreme tidal forces at the bubble's boundary. While the interior remains calm, the shell itself is a region of intense curvature. Matter passing through it would be subjected to enormous stresses. This effectively isolates the interior from the exterior. The bubble is not something one casually enters or exits while in motion. The energy requirements, as initially calculated, were overwhelming. The shell demanded negative energy densities so large that the total required energy exceeded that of massive astronomical bodies. This immediately placed the concept beyond any foreseeable technology. But theoretical physics does not discard ideas solely because they are impractical. It asks whether the requirements are fundamental or contingent. Are they unavoidable, or are they artifacts of a particular mathematical choice? This question sparked years of further work. Researchers explored modified bubble shapes that reduced energy demands by spreading curvature over larger regions. Others examined whether quantum effects could supply negative energy more efficiently. Still others asked whether alternative theories of gravity might permit similar geometries with less extreme conditions. Each approach revealed trade-offs. Reducing energy density often increased the size of the affected region. Smoothing the bubble reduced peak requirements but made containment more difficult. Introducing quantum effects brought new constraints from quantum inequalities that limit how negative energy can be distributed. What emerged was not a path to construction, but a deeper understanding of space-time's resistance to manipulation. Space-time is flexible, but not easily persuaded. This resistance may itself be a form of cosmic stability, a way of preventing small-scale disturbances from cascading into global catastrophes. The same equations that permit exotic solutions also impose safeguards that make them extraordinarily difficult to realize. In this sense, the Alcubierre concept sits at the edge of permissibility. It is allowed, but barely. Its importance lies not in what it enables today, but in what it teaches. It shows that faster-than-light effects are not categorically forbidden by relativity. It shows that geometry can substitute for motion. It shows that the universe's deepest laws are more subtle than simple prohibitions. It also shows that permission does not imply accessibility. Physics is filled with such boundaries. Absolute zero can be approached but never reached. Perfect efficiency is defined, but unattainable. Singularities are predicted, but hidden behind horizons. Warped space-time travel may belong to this same class, an idea that illuminates the structure of reality without offering a practical path forward. Or it may be a starting point. The Alcubierre metric did not close the discussion. It opened it. It gave physicists something concrete to analyze, criticize, and refine. It turned speculation into calculation. In doing so, it reshaped the conversation about faster-than-light travel from fantasy to geometry. The Alcubierre concept. Revisited. As soon as the Alcubierre metric entered the literature, it attracted a particular kind of attention. Not excitement in the popular sense, but scrutiny. Physicists began probing it not for how inspiring it was, but for how fragile it might be. Every assumption was examined. Every mathematical choice was questioned. The goal was not to dismiss the idea, but to understand exactly where its limits lay. In theoretical physics, this process is how ideas mature. One of the first realizations was that the original Alcubierre solution was not unique. It was one member of a broader class of space-time geometries capable of producing similar effects. The specific shape of the bubble, the thickness of its boundary, and the way curvature was distributed were not fixed by necessity. They were choices. This opened a new line of inquiry. If the geometry could be altered, perhaps the most extreme requirements were not fundamental, but artifacts of an early, simplified model. Researchers began experimenting with alternative space-time profiles. Some proposed stretching the bubble asymmetrically. Others explored flattening the curvature gradients to avoid sharp transitions. Still others considered multi-layered shells, where space-time distortion was distributed across several regions rather than concentrated in one. Each variation changed the balance of demands. In some cases, peak negative energy densities were reduced, but only by increasing the total amount of exotic energy required. In others, the total energy dropped, but the affected volume grew to impractical scales. Trade-offs appeared everywhere. This pattern was not discouraging. It was revealing. It suggested that the Alcubierre metric was not an isolated curiosity, but a window into a broader principle. Space-time manipulation is possible in theory, but it resists being optimized. Improvements in one area tend to worsen conditions elsewhere. This resistance hints at a deeper structure within the laws of physics. Constraints that emerge not as explicit prohibitions, but as balancing acts. One of the most influential critiques came from quantum field theory. While negative energy does exist in limited contexts, it is tightly constrained by what are known as quantum inequalities. These inequalities limit both the magnitude and duration of negative energy that can exist in any given region. In simple terms, the universe allows small loans of negative energy, but it demands rapid repayment with interest. These constraints pose serious challenges for any macroscopic spacetime bubble. The amounts of negative energy required and the timescales over which they must be sustained appear to exceed what quantum fields can provide under known laws. This does not automatically invalidate the concept. Quantum inequalities are derived within specific frameworks and assumptions. They apply to known quantum fields in flat or gently curved spacetime. Whether they remain absolute under extreme curvature or in unknown regimes remains an open question. Nevertheless, they act as a powerful warning. Another issue concerns stability. Even if the energy requirements could somehow be met, would the space-time bubble remain intact? Small perturbations in space-time geometry can grow rapidly. In many exotic solutions to Einstein's equations, tiny fluctuations lead to catastrophic collapse or runaway expansion. The Alcubierre bubble is no exception. Analyses suggest that maintaining the bubble would require extraordinary precision. Any asymmetry in the energy distribution could distort the geometry in unpredictable ways. Instead of transporting its occupant, the bubble could shear, fragment, or generate intense gravitational radiation. This instability is not merely technical. It reflects the fact that space-time is not a passive medium. It reacts dynamically to changes, and those reactions can amplify rather than damp disturbances. There is also the issue of interaction with external matter. A moving space-time bubble would encounter particles, radiation, and fields along its path. These would not simply pass through unaffected. The bubble's geometry would compress incoming radiation at its leading edge, potentially concentrating enormous energies in a narrow region. Some analyses suggest that upon arrival, this accumulated energy could be released catastrophically, posing severe risks to both the destination and the bubble's occupant. Again, these are not engineering oversights. They are consequences of the geometry itself. The more physicists explored these challenges, the clearer the picture became. The Alcubierre concept was not pointing toward an imminent technology. It was pointing toward a boundary in our understanding of space-time. That boundary lies between what the equations allow in principle and what the universe permits in practice. Yet even as obstacles multiplied, the idea did not fade. Instead, it evolved. Some researchers began to view the bubble not as a vehicle, but as a probe, a way to test the limits of general relativity and its compatibility with quantum theory. If space-time could be warped in such extreme ways mathematically, then any complete theory of physics would need to explain why such configurations are suppressed, unstable, or forbidden in reality. Others explored whether similar effects could arise naturally, without deliberate engineering. Certain cosmological models predict regions of space-time with unusual geometry. Cosmic strings, hypothetical defects left over from the early universe, could in theory produce localized space-time distortions. Whether these distortions resemble anything like a warp bubble remains speculative, but the comparison is instructive. The Alcubierre metric also influenced thinking beyond faster-than-light travel. It sharpened discussions about energy conditions, assumptions about the behavior of matter and energy that underlie many theorems in relativity. By explicitly violating some of these conditions, the metric forced physicists to confront which assumptions were truly fundamental and which were convenient simplifications. In this way, the concept acted as a stress test for the theory itself. Perhaps most importantly, it reframed the question of faster-than-light travel. Instead of asking whether it could be built, physicists began asking what it would mean for space-time to allow such configurations at all. Why does relativity permit these solutions if they are so difficult to realize? Are they mathematical artifacts? Or do they point toward deeper principles not yet understood? Physics has encountered similar questions before. Black holes were once dismissed as pathological solutions, mathematical oddities with no physical relevance. Only later did they become central to astrophysics. Wormholes, too, occupy an ambiguous space between geometry and plausibility. The Alcubierre bubble now sits among these ideas. It is neither accepted as a realistic possibility nor rejected as meaningless. It exists in a liminal space, permitted, problematic, and profoundly informative. What it teaches is not how to travel faster than light, but how space-time itself can behave when pushed to extremes. It reveals that the universe's rules are not simple walls, but intricate landscapes shaped by trade-offs, balances, and hidden constraints. In exploring those landscapes, physics often discovers more than it set out to find. New mathematical models suggest extreme speeds. When an idea survives sustained criticism, it does not remain unchanged. It fragments, mutates, and reappears in new forms, shaped by the pressure of unanswered questions. The Alcubierre concept, once introduced, became less a destination and more a point of departure. Physicists began to ask not how to perfect that specific geometry, but whether its most troubling features were essential, or merely inherited from the way the problem was first posed. This shift marked a quiet transition in the field. The focus moved away from a single space-time bubble and toward a broader investigation of how space-time might be engineered, constrained, or coaxed into extreme configurations without collapsing under its own demands. The central question was no longer whether one particular model worked, but whether the underlying principle, effective faster-than-light displacement via space-time deformation, could emerge in other mathematical guises. General relativity does not provide a unique answer to how space-time must behave under a given circumstance. It provides a framework. Within that framework exists a vast space of possible geometries, most of them unexplored. The Alcubierre metric illuminated one narrow corridor through that space. New models began probing adjacent regions. Some approaches started by relaxing assumptions that had gone unquestioned. The original bubble geometry assumed a specific symmetry and a sharp separation between interior and exterior regions. What if space-time deformation did not need to be so abrupt? What if the transition between flat and curved regions could be gradual, diffuse, or layered? Mathematically, this meant trading intensity for extent. Instead of concentrating extreme curvature into a thin shell, newer models spread smaller distortions across larger volumes. The resulting configurations no longer resembled a compact bubble moving cleanly through space. They were messier, more subtle and less intuitive, but they demanded less extreme local energy densities. In these models, effective motion emerged not from a single dramatic space-time feature, but from the cumulative effect of many mild distortions working together. The result was not elegance, but possibility. Other researchers approached the problem from a different direction entirely. Rather than modifying space-time geometry directly, they asked whether known physical fields could naturally produce space-time behavior resembling warp-like motion under extreme conditions. This line of thought drew inspiration from analog systems, physical setups that mimic aspects of general relativity in non-gravitational contexts. Fluids, optical media, and condensed matter systems can all exhibit effective horizons, curved trajectories, and signal propagation limits that resemble those found in space-time physics. These analogs do not reproduce gravity itself, but they offer insight into how complex behavior can emerge from relatively simple rules. In some cases, researchers found that effective faster-than-light signal propagation could occur in these systems without violating their internal causal structure. The signals were not outrunning their medium's fundamental speed limit. Instead, the medium itself was changing. The parallel to space-time warping was impossible to ignore. This did not suggest that interstellar travel could be achieved with laboratory fluids or metamaterials. It suggested something subtler, that systems governed by local constraints can still produce global behavior that appears to evade those constraints. If such behavior is common in complex systems, space-time may be no exception. Another avenue of exploration involved revisiting the role of coordinate systems. In general relativity, how motion appears depends critically on how space-time is described. Certain coordinate choices can make spacetime appear static, while others reveal dynamic behavior hidden beneath the surface. Some researchers asked whether faster-than-light effects might emerge not from exotic energy, but from reinterpreting known solutions in unfamiliar coordinates. This approach did not eliminate the need for extreme conditions, but it sharpened the conceptual picture. It highlighted how deeply human intuition is tied to particular ways of slicing space-time into space and time, and how misleading those slices can be. In certain coordinate systems, space-time itself can appear to flow, dragging objects along without them moving locally at all. These flows do not represent physical rivers of space, but they capture something real about how geometry evolves. Such descriptions reinforce the idea that speed is not always the most meaningful quantity in relativistic physics. Geometry often matters more. Perhaps the most provocative developments came from attempts to combine general relativity with quantum field theory more directly. While a complete theory of quantum gravity remains elusive, physicists can explore semi-classical regimes where quantum fields exist on curved space-time backgrounds. In these regimes, vacuum energy is no longer a passive backdrop. It becomes an active participant. Quantum fields respond to curvature, boundaries, and motion. They produce effects like particle creation, vacuum polarization, and energy redistribution. In extreme geometries, these effects can become significant. Some models suggested that under carefully arranged conditions, quantum vacuum effects might amplify space-time distortions rather than suppress them. Instead of acting as a stabilizing influence, quantum fluctuations could, in principle, reinforce certain geometric patterns. These ideas remain speculative. They depend on extrapolations into regimes where known theories are strained. But they represent a shift in attitude. Rather than treating quantum effects as obstacles to space-time manipulation, some researchers began asking whether they could be allies. This is a delicate line of inquiry. Quantum field theory is constrained by powerful principles that protect causality and stability. Any amplification mechanism must respect those principles or risk inconsistency. But the mere possibility that quantum effects could participate in shaping space-time at macroscopic scales reopened questions that had seemed closed. Another class of models explored modifications to gravity itself. General relativity has passed every experimental test to date, but it is not assumed to be the final word. Many alternative theories of gravity have been proposed, motivated by cosmology, unification, or mathematical consistency. In some of these theories, space-time responds differently to energy and momentum. In particular, certain models allow space-time to become more responsive or less stiff under extreme conditions. In such frameworks, the energy required to produce a given curvature could be lower than in Einstein's theory. These modifications are tightly constrained by observation. Any viable theory must reproduce general relativity's predictions in familiar regimes. But outside those regimes, new behavior may emerge. Some of these alternative theories permit warp-like solutions with reduced exotic energy requirements. Others eliminate certain instabilities present in the original Alcubierre metric. None provide a clear path to construction, but they expand the conceptual landscape. They suggest that the difficulty of space-time manipulation may be contingent on the details of gravity itself, not an absolute feature of reality. This possibility is both exciting and sobering. If true, it implies that our current understanding of space-time may be incomplete in precisely the regimes relevant to extreme travel concepts. It also implies that resolving these questions requires progress in fundamental physics, not engineering. Across all these approaches, a common theme emerges. No model offers a shortcut. No equation suddenly makes faster-than-light travel easy. What they do offer is nuance. They reveal that the original Alcubierre concept was not a dead end and but a first approximation, a rough sketch of what might be geometrically possible. By exploring variations, extensions, and alternatives, physicists have begun mapping a region of theoretical space that was previously invisible. In this region, effective speeds far exceeding that of light are not immediately ruled out. They arise as emergent properties of complex space-time behavior rather than as violations of fundamental limits. This reframing matters. It shifts the conversation from, "Can we break the speed of light?" to, "What does the speed of light actually limit?" The answer, increasingly, is local behavior, not global outcomes. Space itself can behave in ways that produce extreme displacement without requiring extreme motion. At the same time, these models reinforce how difficult such behavior is to sustain. Every path toward reduced energy demands introduces new complications. Every relaxation of one constraint tightens another. Stability, control, causality, and consistency remain stubborn obstacles. This pattern suggests that the universe may be finely balanced. It allows extraordinary configurations, but only at the edge of feasibility. The laws do not prohibit such arrangements outright, but they do not encourage them either. From a philosophical perspective, this is revealing. It implies that the universe is not optimized for traversal. It is optimized for coherence. Structures that threaten that coherence, by destabilizing causality or energy balance, are permitted mathematically but suppressed physically. Yet suppression is not the same as prohibition. Physics has repeatedly shown that phenomena once thought unreachable can become accessible when deeper principles are understood. The harnessing of nuclear energy, the detection of gravitational waves, and the manipulation of quantum states all emerged from theoretical insights long before practical realization. Whether space-time engineering will follow this trajectory remains unknown. What is clear is that the mathematical landscape is richer than it once appeared. Faster-than-light effects are no longer confined to a single controversial metric. They appear in various forms across a range of theoretical explorations, not as promises, as possibilities. New mathematical models suggest extreme speeds. As theoretical models multiplied, a pattern became increasingly clear. No matter how creatively space-time was reshaped, no matter how gently curvature was distributed or how cleverly equations were arranged, the same obstacle kept returning in different forms. The mathematics consistently demanded something beyond ordinary matter and familiar energy. That requirement did not arise from a single assumption or a specific metric. It emerged from the structure of space-time itself. At the center of this challenge lies a set of principles known as the energy conditions. These are not laws in the same sense as conservation of energy or the speed of light limit. They are assumptions, statements about how matter and energy are expected to behave under normal circumstances. In classical general relativity, these conditions ensure that gravity behaves predictably, that mass attracts rather than repels, and that space-time remains stable. Most everyday matter obeys these conditions effortlessly. Warp-based models do not. To compress space ahead of a region while expanding it behind, space-time must respond to a stress-energy distribution unlike anything produced by conventional matter. The equations demand pressures and energy densities that are negative relative to the vacuum. They require space-time to curve in a way that ordinary mass cannot produce. This is not a flaw of a particular model. It is a recurring feature across almost every theoretical approach to effective faster-than-light displacement. Negative energy is not merely convenient. It appears essential. In quantum physics, the vacuum is not empty. It is the lowest energy state of a field, filled with fluctuations that cannot be eliminated. Under certain conditions, these fluctuations can be altered, producing regions where the local energy density drops below that of the surrounding vacuum. This phenomenon is subtle, constrained, and fleeting, but it is real. One of the most well-known examples is the Casimir effect. When two conducting plates are placed extremely close together in a vacuum, certain quantum fluctuations are suppressed between them. The result is a measurable force, arising from a difference in vacuum energy density. This effect does not create large amounts of negative energy, nor does it provide a practical source of exotic matter. But it demonstrates something crucial. The vacuum is malleable. General relativity does not distinguish between energy from matter and energy from vacuum fluctuations. Curvature responds to both. If quantum fields can, even briefly, produce regions of negative energy, then space-time can, in principle, respond to those regions. The difficulty lies in scale and duration. Quantum inequalities place strict limits on how much negative energy can exist, how long it can persist, and how it must be balanced by positive energy elsewhere. These constraints are not arbitrary. They arise from deep principles in quantum field theory that protect causality and stability. Any attempt to accumulate large amounts of negative energy in a macroscopic region runs into these limits quickly. This creates a tension between general relativity and quantum theory. Relativity permits exotic space-time geometries. Quantum theory restricts the energy configurations required to support them. Some physicists interpret this tension as evidence that warp-based travel is effectively forbidden by the deeper structure of physics. Others see it as a sign that our understanding of quantum fields in extreme space-time conditions is incomplete. History offers caution on both sides. Before the development of quantum electrodynamics, vacuum behavior was poorly understood. Effects that seemed impossible later became routine. At the same time, some constraints, such as the impossibility of perfectly isolating a system from quantum noise, have proven fundamental. The question, then, is whether negative energy constraints are absolute or contingent. One line of research explores whether negative energy could be distributed in highly dynamic ways, oscillating rapidly in time or arranged in complex spatial patterns that evade simple bounds. Another investigates whether interactions between multiple fields could produce effective behavior not apparent in single-field models. These approaches are speculative and mathematically demanding. They push known theories to their limits without quite breaking them. A parallel effort examines whether the requirement for negative energy is itself an artifact of classical gravity. In modified theories of gravity, or in frameworks that include additional dimensions, the relationship between energy and curvature can change. In some higher dimensional models, space-time curvature in our familiar dimensions can arise from geometry in extra dimensions, reducing the need for exotic local energy densities. In others, effective negative energy appears as a projection of otherwise ordinary physics. These ideas remain untested and, in many cases, unfalsifiable with current technology. But they serve an important role. They prevent the discussion from collapsing into premature conclusions. Another perspective comes from cosmology. The universe itself appears to be dominated by something that behaves like negative pressure, dark energy. This mysterious component drives the accelerated expansion of space and constitutes the majority of the universe's energy budget. Dark energy is not negative energy in the simple sense required by warp models, but it demonstrates that the universe contains stress energy configurations, unlike anything encountered in laboratory physics. The existence of dark energy weakens the argument that exotic stress energy is inherently unphysical. It suggests that our inventory of what is normal may be incomplete. Still, dark energy does not solve the problem. Its effects are diffuse gentle and uniform. Warp-based geometries demand localized, intense, and precisely shaped energy distributions. This gap remains vast. As these investigations progressed, a sobering realization took hold. Even if the energy requirements could somehow be met, the control problem would remain. Negative energy configurations are not only difficult to create, they are difficult to stabilize. Quantum fluctuations, external perturbations, and internal feedback effects all threaten to disrupt carefully arranged space-time geometries. Maintaining such configurations would require levels of precision far beyond anything currently imaginable. In this light, negative energy becomes more than a resource problem. It becomes a conceptual barrier. It forces physicists to confront the possibility that space-time is protected by deeper principles. Principles that allow exotic solutions mathematically, but suppress them dynamically. This idea resonates with other features of physics. Singularities are predicted but hidden behind horizons. Vacuum decay is possible but extraordinarily rare. Certain symmetries are allowed but broken only under extreme conditions. Warp-based space-time manipulation may belong to this class of phenomena. Not impossible, but guarded. Yet even guarded phenomena can teach us something. By probing where energy conditions fail, physicists learn which assumptions are truly fundamental. By exploring the limits of vacuum behavior, they uncover connections between gravity and quantum theory that might otherwise remain hidden. The pursuit of faster-than-light effects thus becomes a tool rather than a goal. It exposes fault lines in our theories, revealing where classical intuition breaks down and where new physics might emerge. In this sense, the challenge of negative energy is not merely an obstacle. It is a signpost. It marks the boundary where our current frameworks strain and where future insights may be required. What faster than light would do to time. In physics, space and time are never separate for long. Any attempt to alter one inevitably disturbs the other. This is not a philosophical claim, but a mathematical one. In relativity, distance and duration are woven together into a single structure. To compress space is also to reshape time. To accelerate geometry is to distort causality. This is why discussions of faster-than-light effects always drift toward time, even when no one intends them to. At first glance, warp-based space-time travel seems to avoid the classic time paradoxes of superluminal motion. Nothing inside the bubble moves faster than light. No signal locally outruns causality. Clocks inside the bubble tick normally. From the traveler's perspective, time behaves almost mundanely. But relativity is not governed by local perspectives alone. What matters is how different regions of space-time connect globally. When those connections are rearranged, time can behave in ways that feel deeply counterintuitive, even dangerous. The key issue is simultaneity. In everyday experience, events that occur at the same time feel unambiguous. In relativity, simultaneity depends on motion and geometry. Two events that are simultaneous in one frame of reference may not be simultaneous in another. This is not a quirk of measurement. It is a structural feature of space-time. Faster-than-light effective motion stretches this feature to its limits. When space-time is warped so that distant points become close in terms of travel time, the ordering of events can shift in subtle ways. An arrival can precede a departure, depending on the frame from which the sequence is described. This does not require time travel in the cinematic sense. It arises naturally from the way relativity treats space and time as interchangeable under certain transformations. In ordinary relativistic motion, these effects are small and constrained. The speed of light acts as a barrier that preserves a consistent causal order. Once that barrier is bypassed, globally, if not locally, the protection weakens. This is why faster-than-light signals are traditionally associated with causality violations. If a signal can arrive before it is sent in some frame of reference, then cause and effect lose their universal ordering. Warp-based models tread carefully here. They are designed so that no signal inside the bubble travels faster than light. But the bubble itself can connect regions of space-time that would otherwise be causally distant. This raises a profound question. Can global space-time rearrangement preserve causality even when effective? Superluminal displacement occurs. The answer is not simple. Some analyses suggest that certain warp configurations inevitably allow closed time-like curves, paths through space-time that loop back on themselves in time. These curves do not require deliberate time travel. They emerge as geometric consequences of extreme space-time distortion. A closed time-like curve means that an object could, in principle, return to its own past. This possibility is deeply unsettling, not only philosophically, but physically. Causality underpins every predictive structure in science. Without a consistent ordering of cause and effect, the concept of physical law itself begins to erode. For this reason, many physicists suspect that the universe contains mechanisms that prevent such curves from forming in reality, even if equations permit them mathematically. This suspicion is formalized in what is known as the chronology protection conjecture. It proposes that the laws of physics conspire to prevent macroscopic violations of causality. The conjecture is not proven. It is a statement of expectation rather than derivation. But it reflects a pattern seen throughout physics. When equations allow pathological behavior, additional effects often intervene to suppress it. In the context of warp-based space-time manipulation, these effects could take many forms. Quantum fluctuations might destabilize the geometry before causal loops form. Energy requirements might diverge to infinity as dangerous configurations are approached. Horizons might arise that isolate problematic regions from the rest of space-time. Some evidence supports these ideas. Studies of space-time geometries that permit closed time-like curves often find that they are accompanied by infinite energy densities or uncontrollable instabilities. As one approaches the threshold where causality breaks, the space-time becomes increasingly hostile to matter and fields. This suggests that time itself may be protected by energetic barriers. But the protection is not absolute in theory. Certain solutions to Einstein's equations, rotating universes, traversable wormholes under exotic conditions, do permit causal loops without obvious singularities. These solutions are not known to exist in nature, but they demonstrate that relativity alone does not forbid temporal ambiguity. Warp-based models intersect uncomfortably with this territory. Even if a single warp journey does not produce a time paradox, combinations of journeys can. By chaining warp displacements with ordinary motion, it is sometimes possible to construct scenarios where signals return to their point of origin before they were sent. These constructions are mathematically consistent within classical relativity. Whether they are physically realizable is another matter. The deeper issue is that time is not a passive backdrop. Like space, it responds to geometry. When space-time is stretched or compressed, time flows differently in different regions. These differences accumulate. In warp-based scenarios, the interior of the bubble is largely shielded from extreme temporal effects. But the surrounding space-time is not. Time near the bubble's boundary can behave very differently from time far away. This creates a patchwork of temporal flow rates, stitched together by geometry. From a global perspective, This patchwork can lead to inconsistencies in how events are ordered across regions. The universe does not lose causality locally, but it may lose it globally. This distinction matters because physical law is global. Conservation laws, field equations, and boundary conditions all assume a coherent temporal structure. If that structure fractures, the notion of prediction becomes unstable. This is why time-related concerns loom so large in discussions of faster-than-light effects. They are not side effects. They are central. Yet it is also important to note that time dilation and temporal distortion are already part of known physics. GPS satellites must account for relativistic time shifts to function correctly. Clocks at different altitudes tick at different rates. Time flows differently near massive objects. Warp-based space-time manipulation would amplify these effects dramatically, but it would not introduce something entirely alien. The question is not whether time can be distorted. It can. The question is whether it can be distorted without unraveling causality. Some physicists argue that careful space-time design could avoid the most dangerous configurations. By limiting the speed, duration, or geometry of warp-like effects, one might preserve global causal order. Others argue that any effective faster-than-light displacement inevitably opens the door to temporal paradoxes, no matter how carefully it is arranged. At present, there is no consensus. This uncertainty reflects a deeper gap in our understanding. General relativity and quantum theory both treat time in ways that are internally consistent, but not fully compatible with each other. At extreme regimes, precisely where warp-based effects would operate, that incompatibility becomes unavoidable. In this sense, the time problem is not a flaw of warp models. It is a symptom of a deeper, unfinished story in physics. If time can be bent without breaking, it will require principles not yet known. If it cannot, those principles must explain why geometry is permitted to warp almost freely in space, but not in time. Either way, the investigation points beyond current theory. The possibility that faster-than-light effects might entangle space and time in irreversible ways serves as a reminder. Space-time is not a playground. It is a tightly regulated structure, balanced by constraints that may only reveal themselves when pushed to extremes. Warp-based travel does not merely challenge engineering. It challenges chronology. What faster than light would do to time in physics is often treated as a coordinate, something measured, transformed, and compared across frames. But for living systems, time is also experienced. It governs biological rhythms, chemical reactions, neural processes, and the fragile coherence of consciousness itself. Any serious discussion of extreme space-time manipulation must therefore confront not only abstract causality, but the question of whether anything biological could persist within such conditions. Warp-based space-time models appear, at first glance, to be surprisingly gentle on occupants. Inside the bubble, space-time is designed to remain nearly flat. The occupant follows a geodesic, experiencing no large accelerations. Local clocks tick at ordinary rates. In this narrow sense, the environment inside the bubble resembles ordinary deep space. This feature is often emphasized because it contrasts sharply with conventional relativistic travel, where approaching light speed imposes crushing forces, lethal radiation exposure, and severe time dilation. But survivability is not determined by interior conditions alone. The bubble exists within a larger space-time context, and that context imposes indirect effects. Temporal consistency, environmental isolation, and long-term stability all matter. One of the first concerns is synchronization. Biological systems rely on precise timing at multiple scales. From the oscillations of atomic bonds to the firing patterns of neurons, coherence in time is essential. Even small disruptions can cascade into dysfunction. In warp-based scenarios, the interior of the bubble may be temporarily calm, but it is not temporarily isolated. Its relationship to the external universe is altered. Signals entering or leaving the bubble experience delays, distortions, or complete causal disconnection. This creates a situation where the occupant's internal time remains smooth, but their connection to external time becomes fragmented. From a purely physical perspective, this is not immediately fatal, but from an operational or experiential perspective, it introduces profound complications. Communication with the outside world may be impossible during transit. External reference frames may become inaccessible. The traveler becomes temporarily isolated, not frozen, but detached. This isolation extends beyond communication. The boundary of the bubble is a region of intense space-time curvature. Radiation approaching the bubble from the front is compressed and blue-shifted. Low-energy photons can be transformed into high-energy radiation. Particles can be concentrated into narrow, energetic fronts. While the interior is shielded from direct exposure, the boundary must absorb and manage these effects. Any leakage or instability could introduce dangerous radiation into the interior. Long-term exposure to even small amounts of high-energy radiation can disrupt biological tissue, damage DNA, and degrade neural function. The margins for error are narrow. Then there is the issue of temporal gradients. While the interior space-time may be flat, the transition to the exterior is not. Across the bubble boundary, time flows differently. This creates steep temporal gradients, regions where clocks at neighboring points tick at dramatically different rates. Physics allows such gradients, but biology has never evolved to cope with them. If any biological system were exposed, even indirectly, to such gradients, the effects could be severe. Chemical reactions could desynchronize. Cellular processes could lose coherence. Neural timing could fracture. The bubble is designed to prevent this, but design and reality rarely align perfectly. Another subtle concern is memory and identity. Conscious experience relies on continuity. The brain constructs a narrative self from a sequence of events ordered in time. Extreme space-time manipulation threatens that ordering, not by reversing it, but by fragmenting its global context. If a traveler emerges from a warp journey into a region of space-time whose temporal relationship to the departure point is ambiguous, their memories may no longer align cleanly with external records. Events they remember as recent may be ancient elsewhere. Events that seem distant may be contemporaneous. This mismatch is not inherently harmful, but it poses psychological challenges. Human cognition is deeply anchored to shared temporal frameworks. Dislocation in time, even without paradox, can be destabilizing. These issues are not speculative in the sense of science fiction. They are extrapolations of known effects observed in much milder forms. Astronauts experience circadian disruption in microgravity. Jet lag impairs cognition. Long-duration isolation alters perception of time. Warp-based travel would amplify these effects dramatically. There is also the question of aging. If time inside the bubble flows differently from time outside, the biological aging of the occupant may diverge from that of the rest of the universe. This is not unique to warp-based travel. It is already present in relativistic motion. But the degree and unpredictability could be far greater. Depending on the geometry, a traveler might experience relatively little aging while external time advances significantly, or vice versa. The lack of a simple, predictable relationship complicates any attempt at long-term planning. In addition, there is the issue of causality at the personal scale. If global space-time geometry permits closed time-like curves or near loops, even if the traveler never encounters them directly, the mere possibility raises questions about consistency. Could memories be influenced by events that have not yet occurred? Could information leak backward along distorted space-time paths? Most analyses suggest that such effects would be suppressed or inaccessible to occupants. But the lack of a complete theory makes certainty impossible. At a deeper level, these concerns reflect the fact that biology is an emergent phenomenon, finely tuned to a narrow range of physical conditions. Life evolved in a universe where space-time is relatively gentle, predictable, and globally coherent. Warp-based space-time manipulation pushes far beyond those conditions. It is not obvious that life, as we know it, could remain stable in such an environment indefinitely. That does not mean survival is impossible. It means survival cannot be assumed. Any realistic discussion of extreme space-time travel must therefore consider not only shielding and engineering, but adaptation. Could biological systems be modified to tolerate temporal isolation? Could artificial systems, non-biological intelligences, operate more robustly under such conditions? These questions shift the discussion away from vehicles and toward observers. In some sense, warp-based travel may be less about moving humans across the cosmos and more about moving something else. Probes, instruments, or autonomous systems designed to function without continuous causal integration with their origin. This possibility aligns with a broader trend in exploration. The more extreme the environment, the less suitable humans become as direct participants. Deep space, deep oceans, and high-energy laboratories have already taught this lesson. The intersection of time distortion and biology reinforces it. Warp-based space-time manipulation, if it ever becomes possible, may not be a human experience in the familiar sense. It may be something that happens around us, for us, or on our behalf, rather than something we directly inhabit. This realization tempers the imagination. It suggests that even if the universe permits such travel geometrically, it may not be compatible with the fragile temporal coherence that defines living systems. Could humans survive? This kind of travel survival, in physics, is rarely a single question. It is a convergence of many tolerances, mechanical, thermal, radiative, and structural, all of which must remain within narrow bounds for organized systems to persist. When space-time itself becomes the medium of transport, survival depends not only on the conditions inside the vehicle, but on how those conditions are maintained against an environment that behaves in unfamiliar ways. Warp-based space-time travel appears, at first, to offer a paradoxical gift. By removing conventional acceleration, it seems to eliminate many of the dangers associated with high-speed motion. There are no sustained g-forces pressing bodies into seats. There is no need for constant propulsion. Locally, the interior space-time can be engineered to resemble a quiet region of deep space. This apparent calm has led to the suggestion that survivability might be one of the least problematic aspects of warp-based travel. That impression does not last long under closer examination. The absence of acceleration does not imply the absence of stress. The stresses simply migrate from the traveler to the space-time around them. And those stresses, in turn, exert indirect effects on anything embedded within the geometry. The most immediate concern is structural integrity. The boundary of a space-time bubble is not a wall in the ordinary sense. It is a region of extreme curvature where space-time is compressed and stretched intensely over very short distances. Within this shell, tidal forces can become enormous. Any physical structure interacting with this region, either deliberately or accidentally, would experience differential forces that pull it apart at the atomic level. For a vessel carrying occupants, this creates a strict requirement. The interior must be completely isolated from the boundary. No part of the structure can intersect regions of extreme curvature. The geometry must be precise and stable enough to keep the interior space-time smooth at all times. This is a far more demanding requirement than shielding against radiation or micrometeoroids. It requires maintaining a space-time configuration with extraordinary fidelity. Even small deviations could be catastrophic. Another concern is radiation. As space-time compresses ahead of the bubble, electromagnetic radiation becomes blue-shifted. Photons that begin as harmless background radiation can be transformed into high-energy gamma rays. Particles encountered along the path can be focused and accelerated by the geometry itself. The bubble's boundary acts as a kind of cosmic lens, concentrating energy. This energy must go somewhere. If it accumulates at the leading edge, it creates a reservoir of extreme radiation that moves with the bubble. Upon arrival or deceleration, this energy could be released suddenly, bathing the surrounding region in lethal radiation. For occupants, this presents a dual hazard. First, any leakage of radiation into the interior could be fatal. Second, the act of stopping or collapsing the bubble could expose them to a burst of energy unlike anything encountered in conventional spaceflight. Shielding against such effects is not straightforward. Traditional materials interact with radiation through absorption and scattering. Space-time curvature interacts by redirecting and concentrating energy at a geometric level. This suggests that survivability depends not only on material science, but on space-time control itself. Thermal considerations also arise. Energy concentrated at the bubble boundary can generate intense heating. If this heat is not dissipated or redirected, it could destabilize the space-time configuration or bleed into the interior. Biological systems are exquisitely sensitive to temperature. Even small deviations sustained over time can cause irreversible damage. Maintaining thermal stability within a dynamically warped space-time is a non-trivial challenge. Then there is the question of mechanical coherence. Human bodies are not rigid objects. They are collections of fluids, soft tissues, and delicate structures held together by relatively weak forces. Even in environments that feel calm, subtle gradients can produce harmful effects over time. In microgravity, fluids redistribute. Bones lose density. Muscles atrophy. These changes occur despite the absence of crushing forces. Warp-based travel introduces new kinds of gradients, spatial, temporal, and gravitational, that have no direct analog in known environments. The long-term biological response to such conditions is unknown. Even if acute injury is avoided, chronic effects could accumulate. Another layer of complexity involves perception and orientation. Human sensory systems evolved in a gravitational field with stable spatial cues. Vision, balance, and proprioception rely on consistent relationships between motion, force, and time. Inside a space-time bubble, many of these cues could be altered or absent. The absence of acceleration may prevent nausea, but the lack of consistent external reference frames could induce disorientation. Extended exposure to such conditions could affect cognition, mood, and decision-making. These are not trivial considerations. Survival is not merely about avoiding death. It is about maintaining functional coherence over time. The question becomes whether humans could adapt. Adaptation is possible within limits. Humans can acclimate to microgravity, radiation exposure, and isolation, given sufficient time and support. But adaptation presupposes stability. It requires an environment that remains within a consistent envelope. Warp-based spacetime manipulation threatens to push conditions beyond that envelope. This has led some researchers to suggest that survival might require more than protection. It might require transformation. One possibility is heavy reliance on artificial systems. Life support environments could be fully sealed, insulated not only from radiation and temperature, but from space-time gradients themselves. Occupants could be placed in suspended states, reducing metabolic demands and sensitivity to temporal distortions. Another possibility is that biological occupants would be replaced entirely by non-biological ones. Artificial intelligences, autonomous probes, or hybrid systems might tolerate conditions that biological organisms cannot. They would not require coherent circadian rhythms, stable neural timing, or psychological continuity. In this view, warp-based travel becomes a tool for information transfer rather than human transport. This is not a concession of defeat. It reflects a recurring pattern in exploration. As environments become more extreme, the role of direct human presence diminishes. Humans send instruments where they cannot go themselves. Warp-based spacetime travel, if ever realized, may represent the ultimate extension of this pattern. There is also the possibility that future biological forms, engineered or evolved, could tolerate conditions that humans cannot. This remains speculative, but it underscores the fact that survivability is not a fixed property. It depends on the organism. What remains clear is that survival is not guaranteed by the apparent calm of the interior spacetime alone. It depends on a web of interacting factors: geometry, energy flow, stability, and biological tolerance. Each of these factors introduces uncertainties that compound rather than cancel. From a scientific perspective, these uncertainties are not reasons to abandon the discussion. They are reasons to refine it. Understanding survivability in extreme space-time conditions informs not only speculative travel concepts, but our broader understanding of life's relationship with the universe. It reveals how tightly life is coupled to the structure of space-time itself. Life is not just in space and time, it is shaped by them. If space-time can be radically altered, then the conditions for life may be far narrower than geometry alone would suggest. Could humans survive this kind of travel? Survival does not end at arrival. In many ways, arrival is where the most subtle dangers begin. A space-time bubble, if it could be created and sustained, would not simply deposit its contents gently into an unchanged universe. It would interact with its destination in ways that ripple outward, altering local conditions long after the journey itself had ended. The universe does not easily forget disturbances in its geometry. When a warp-like configuration collapses or dissipates, the energy stored in its curved space-time must be released or redistributed. Curvature does not vanish quietly. It relaxes, radiates, and reconfigures. This process can generate gravitational waves, bursts of radiation, or abrupt changes in local space-time structure. For a traveler, this means that arrival may be more dangerous than transit. If the accumulated energy at the bubble's boundary is released too quickly, the destination region could be flooded with high-energy radiation. Nearby matter, interstellar gas, dust, even planetary atmospheres could be ionized or heated violently. The very act of arrival could resemble a localized astrophysical event rather than a gentle landing. This is not a question of poor design. It is a consequence of how energy and geometry behave. The traveler's vessel would need to be insulated not only from external radiation, but from the aftermath of its own journey. The timing, location, and manner of bubble dissipation would be critical. A miscalculation could render the destination uninhabitable, at least temporarily. This raises an ethical dimension rarely discussed. If warp-based travel were possible, its use would carry responsibility beyond the traveler. Arriving near a star system, a planet, or any region of structured matter could pose risks to existing environments. The geometry of space-time does not respect boundaries drawn by biology or civilization. Even a successful journey could leave scars. From the perspective of survivability, this means that humans would not only need protection during travel, but assurance that arrival conditions remain within tolerable limits. That assurance would require predictive control over space-time relaxation processes that are not yet understood. There is also the matter of gravitational interaction. A space-time bubble does not move through a vacuum devoid of structure. It passes through regions shaped by stars, dark matter, and cosmic expansion. These background curvatures interact with the bubble's geometry in complex ways. Near massive objects, space-time is already curved. Superimposing a warp-like distortion on top of this background could produce unpredictable effects. The bubble might shear, tilt, or destabilize as it encounters gradients in gravitational potential. For human occupants, such instabilities could translate into sudden changes in interior conditions. Even if these changes are small in absolute terms, their unpredictability poses a serious risk. Stability is as important as gentleness. Another overlooked aspect of arrival is synchronization with the destination's temporal framework. If the traveler's journey involved significant temporal displacement relative to the external universe, arrival could occur at a time very different from what was expected. This is not merely a matter of aging. It affects environmental conditions. Stars evolve. Planetary atmospheres change. Radiation environments fluctuate. A destination that was safe at departure might be hostile upon arrival. For humans, whose survival depends on narrow environmental windows, this temporal uncertainty compounds the challenge. There is also the psychological dimension of emergence. Humans are not merely physical systems. They are narrative systems. They construct meaning from continuity of place, time, and cause. Emerging from a journey that compresses or rearranges space-time could disrupt that continuity profoundly. The traveler may arrive in a universe that feels disconnected from their origin, not just spatially, but historically. This sense of displacement could have lasting psychological effects, even if physical survival is assured. In this sense, survivability includes identity. The more extreme the manipulation of space-time, the more fragile that identity may become. Some of these challenges might be mitigated through preparation. Extended training, artificial habitats, suspended animation, or gradual reintegration could help preserve coherence. But mitigation assumes predictability. Warp-based space-time travel offers little of that. This leads to a sobering conclusion. Even if the geometry allows such travel, and even if engineering hurdles are overcome, human survivability may remain marginal. Not because the interior of the bubble is inherently lethal, but because the broader space-time context is hostile to biological continuity. Humans evolved to survive within a universe that changes slowly. Warp-based travel exploits regimes where change is rapid, extreme, and non-linear. That mismatch may be fundamental. This does not mean that exploration is impossible. It suggests that the form of exploration must change. Instead of transporting humans, warp-based systems might transport instruments, data, or autonomous agents designed to function without biological constraints. These agents could map distant regions, sample environments, and return information without concern for aging, radiation, or psychological continuity. Human presence, if it occurs at all, might follow later through slower, more conventional means. In this way, warp-based travel becomes a reconnaissance tool rather than a migration pathway. This reframing aligns with the broader trajectory of science. We send probes where we cannot yet go. We let instruments precede us. Only when environments are understood do we consider human arrival. Warp-based space-time manipulation, if it ever becomes more than theory, would likely follow this pattern. Understanding survivability, then, is not about proving that humans could endure such travel. It is about recognizing the limits imposed by biology and respecting them. The universe may permit extreme shortcuts through space-time, but it does not guarantee that life can take them. What this means for the universe: if space-time could be reshaped to allow effective faster-than-light displacement, the most profound consequences would not be technological. They would be cosmological. Such a capability would not merely change how far or how fast something could travel. It would alter how the universe is connected, how regions of space relate to one another, and how the structure of reality itself is understood. Distance in cosmology is not just a measurement. It is a barrier. It defines what can interact, what can influence what, and what remains forever out of reach. The observable universe is bounded not by walls, but by time. The finite age of the cosmos and the finite speed at which information can propagate. Warp-based space-time manipulation challenges this boundary, not by breaking it outright, but by circumventing it geometrically. If regions of space-time can be brought into close causal contact through engineered curvature, then the universe becomes effectively smaller. Vast separations that once defined isolation become traversable. The cosmic horizon, which limits what we can observe or influence, becomes less absolute. This does not mean the universe loses its scale. Galaxies would still be separated by millions of light years. The expansion of space would still stretch distances over time. But the meaning of those distances would change. They would become conditional rather than final. From a cosmological perspective, this would redefine exploration. Regions of the universe currently considered causally disconnected, places light from us will never reach, might become accessible through carefully shaped space-time paths. This would blur the distinction between the observable universe and the universe as a whole. Such a shift would have implications for how cosmology is practiced. Many models rely on the assumption that distant regions cannot influence one another once they cross a cosmological horizon. This assumption underpins ideas about large-scale uniformity, cosmic evolution, and the interpretation of background radiation. If horizons can be bypassed geometrically, those assumptions would need to be revisited. This does not mean they would be wrong. It means they would be incomplete. The universe would no longer be a collection of regions linked only by light-speed-limited signals. It would be a network whose connectivity depends on geometry, energy, and engineering. This raises deep questions about causality on cosmic scales. If a civilization could influence regions beyond its conventional light cone, the global ordering of events becomes more complex. Cause and effect remain local, but their global arrangement can be altered. This does not immediately lead to paradox. It leads to a more intricate causal structure, one where influence is not strictly tied to light-speed propagation through unaltered space-time. Such a universe is not forbidden by physics, but it is unfamiliar. There are also implications for cosmic isolation. One of the great themes of modern astronomy is the loneliness imposed by distance. Even nearby stars are separated by years of travel at conventional speeds. Galaxies are effectively unreachable. Civilizations, if they exist elsewhere, are likely isolated not by hostility, but by physics. Warp-based space-time manipulation would weaken that isolation. The universe would become more permeable. The silence of the cosmos would take on new meanings. Absence of contact would no longer imply impossibility. It would imply choice, rarity, or restraint. This reframing carries both promise and caution. Increased connectivity does not guarantee harmony. It introduces the potential for interaction on scales that were previously self-contained. Actions taken in one region could have consequences far beyond what was once possible. This is why many physicists view such possibilities with ambivalence. The same geometry that allows exploration also allows interference. From a universal perspective, the question becomes whether space-time itself resists such connectivity for a reason. The enormous energy requirements, stability issues, and causal risks associated with warp-based travel may not be accidents. They may function as natural safeguards, preserving the large-scale coherence of the universe by making extreme shortcuts extraordinarily difficult. In this view, the universe is not designed for convenience. It is designed for consistency. Warp-based space-time manipulation, if possible at all, would represent an exception carved into that consistency, a deliberate bending of rules that normally protect cosmic order. There are also implications for the early universe. During inflation, space expanded faster than light, separating regions that were once in close contact. This expansion smoothed the universe, erased initial irregularities, and set the stage for cosmic structure. If space-time manipulation allows local analogs of this process, it suggests a deep continuity between cosmology and engineering. The same principles that shaped the universe at its birth could, in principle, be invoked deliberately on much smaller scales. This connection is unsettling and profound. It implies that the distinction between natural and artificial space-time dynamics may be less sharp than we assume. The universe has already demonstrated the capacity for extreme geometric behavior. Warp-based concepts simply ask whether that behavior can be localized and controlled. There is also a philosophical consequence. If distance is no longer an absolute barrier, then remoteness loses some of its meaning. The universe becomes less about separation and more about structure. Accessibility depends on knowledge and capability rather than sheer scale. This shifts humanity's relationship with the cosmos. Exploration becomes less a matter of endurance and more a matter of understanding. The limits are no longer defined solely by how fast we can go, but by how well we grasp the geometry of reality. At the same time, this perspective emphasizes humility. The universe permits extraordinary configurations, but it does not yield them easily. Every path toward extreme connectivity is lined with constraints that appear finely tuned to prevent misuse or instability. This suggests that any civilization capable of manipulating space-time on such scales would need not only technological mastery, but deep restraint. The stakes would be cosmic. Warp-based space-time travel would not merely be a new mode of transportation. It would be a new way of participating in the universe, one that carries responsibilities commensurate with its power. What this means for the universe. When physics confronts the possibility of extreme space-time manipulation, it inevitably turns inward. Not toward technology, but toward meaning. Ideas like warp warp-based travel force a reconsideration of what the universe permits? And perhaps more importantly, why those permissions exist at all? The laws of physics do not merely describe what happens. They define a landscape of allowed behaviors, most of which are never realized. Within that landscape, some configurations are common and stable. Others are rare, fragile, and fleeting. Warp-like space-time geometries belong to the latter category. Their existence in the equations is not an accident. General relativity does not forbid dramatic rearrangements of space and time. It allows them, but only at the cost of extreme conditions. This balance, permission paired with resistance, appears again and again in fundamental physics. Singularities are allowed, but hidden. Vacuum decay is possible, but suppressed. Perfect symmetry is permitted, but often broken. The universe seems to acknowledge extreme possibilities while surrounding them with barriers. Warp-based space-time manipulation fits this pattern precisely. From a cosmological standpoint, this suggests that faster-than-light effects are not aberrations, but edge cases. They exist at the boundaries of what space-time can do without tearing itself apart. Those boundaries matter. They define the difference between a universe that is merely large and one that is fundamentally connected. They determine whether cosmic isolation is an absolute feature or a contingent one. If the universe were structured such that no space-time shortcuts were even mathematically possible, then distance would be a permanent, defining feature of reality. The cosmos would be not only vast, but irreducibly fragmented. Instead, the equations whisper something else. They suggest that connectivity is possible in principle, but only under conditions that demand extraordinary coherence, energy control, and precision. This implies a universe that values consistency over convenience, but does not prohibit ingenuity. There is a subtle generosity in this structure. The universe does not present itself as a locked system with unreachable regions forever sealed away, nor does it offer easy passage. It offers a challenge, one that can be contemplated long before it can be met. This has implications for how civilizations might evolve. A civilization capable of manipulating space-time on extreme scales would not simply be advanced in an engineering sense. It would need an intimate understanding of geometry, energy, causality, and stability. It would need to navigate trade-offs rather than brute force solutions. In this light, warp-based space-time travel becomes less a test of power and more a test of restraint. Any misuse of such capabilities could destabilize environments, disrupt causal order, or introduce irreversible changes to cosmic structure. The risks scale faster than the benefits. This may explain why the universe makes such capabilities so difficult to realize. It may not be a prohibition, but a filter. Only civilizations that understand the consequences deeply enough to avoid catastrophic misuse could hope to approach these regimes safely. This idea echoes a broader theme in astrobiology and cosmology. The absence of visible cosmic engineering may not reflect a lack of intelligence, but a convergence toward caution. Extreme technologies, if they exist at all, may be used sparingly, quietly, or not at all. From this perspective, the silence of the universe acquires a new interpretation. Not emptiness, but discretion. Warp-based space-time manipulation also reframes the idea of exploration. Rather than scattering indiscriminately across the cosmos, exploration becomes a deliberate act constrained by ethical and physical considerations. The universe is not a frontier waiting to be crossed. It is a structure waiting to be understood. This reframing has consequences for human aspiration. For centuries, progress has been associated with speed. faster ships, faster communication, faster computation. Warp-based concepts tempt us to extend that trajectory indefinitely. But the physics suggests a different lesson. Extreme scales. Progress may not mean going faster. It may mean choosing carefully when not to. The ability to manipulate space-time would grant access not only to distant places, but to new responsibilities. Intervening in cosmic geometry is not a neutral act. It reshapes causal relationships that may have evolved over billions of years. Even small interventions could propagate in unexpected ways. This awareness tempers triumphal narratives. It suggests that the ultimate significance of faster-than-light possibilities lies not in how they might be used, but in how they shape our understanding of limits. The universe appears to permit extraordinary shortcuts, but only in forms that force deep engagement with the nature of reality. It does not reward impatience. In this sense, warp-based space-time manipulation is less a promise of escape from cosmic distance and more a mirror held up to our theories. It reveals how much we still do not understand about energy, geometry, and time. It exposes the seams where general relativity and quantum theory meet and strain against one another. The fact that these ideas remain unresolved is not a failure. It is an invitation. They invite deeper theories, frameworks that unify gravity and quantum mechanics, clarify the role of vacuum energy, and explain why certain configurations are permitted but suppressed. They invite humility. The universe is not obligated to be navigable on human terms. That it even hints at such navigability is remarkable. As the discussion approaches its conclusion, one final perspective remains to be examined. If faster-than-light space-time manipulation is not a breakthrough waiting to happen, but a boundary condition waiting to be understood, what does that say about where we are now? Are we standing on the edge of a revolution, or merely at the edge of comprehension? Why this is still the beginning, not the breakthrough. When ideas persist without becoming technologies, it is tempting to regard them as failures. In science, however, endurance often signals something more important. Concepts that refuse to disappear usually do so because they touch a real feature of the universe, one that is not yet fully understood. Warp-based faster-than-light travel belongs to this category. It has not advanced because of engineering breakthroughs. It has advanced because each attempt to dismiss it reveals something deeper about space-time, energy, and the limits of physical law. The idea remains alive not because it promises results, but because it continues to expose gaps in our understanding. This is what places it at the beginning, not the end. General relativity, despite its success, is an incomplete theory. It describes space-time with extraordinary precision, yet it does so without reference to quantum mechanics. It treats geometry as smooth and continuous, even though every other fundamental aspect of reality appears quantized. Warp-based solutions sit precisely at this fault line. They rely on classical space-time behaving in extreme ways while simultaneously invoking quantum effects to supply exotic energy conditions. This uneasy partnership highlights the absence of a unified framework, a theory that explains how space-time behaves when gravity and quantum fields are both strong. As long as that framework is missing, ideas like faster-than-light space-time manipulation cannot be resolved conclusively. They cannot be ruled out, and they cannot be realized. They exist in a state of suspended judgment. This is not a weakness of physics. It is a reflection of where understanding currently stands. Historically, similar situations have marked the approach of deeper revolutions. Before quantum mechanics, atoms were understood through classical models that worked imperfectly and failed spectacularly under certain conditions. Before relativity, Newtonian gravity explained nearly everything, until it didn't. In each case, unresolved edge cases pointed the way forward. Warp-based space-time manipulation is an edge case of this kind. It reveals where general relativity permits behavior that feels physically unreasonable, and where quantum theory intervenes without fully explaining why. The tension between permission and suppression suggests that a deeper principle is at work, one not yet articulated. This is why the discussion continues. Not because physicists believe faster-than-light travel is imminent, but because they believe understanding why it is so difficult may reveal something fundamental about the universe. There is also a shift in how progress is measured. Early discussions of warp-based travel often asked how much energy would be required, how large the bubble would be, or how fast it could go. These questions assume that the basic framework is sound and merely awaits refinement. More recent work asks different questions. Why does space-time respond so stiffly to certain deformations? Why are negative energy configurations so constrained? Why do attempts to bypass causal limits consistently generate instabilities or horizons? These are not engineering questions. They are structural ones. They suggest that space-time may possess built-in regulatory mechanisms, features that emerge only when extreme conditions are approached. These mechanisms are not explicitly encoded as prohibitions. They arise dynamically through feedback between geometry, energy, and quantum effects. If such mechanisms exist, they could explain why the universe appears permissive in theory, but conservative in practice. Understanding them would have consequences far beyond faster-than-light travel. It would inform black hole physics, early universe cosmology, vacuum stability, and the nature of time itself. In this sense, warp-based concepts act as diagnostic tools. They probe the limits of existing theories in ways that more familiar phenomena cannot. They force physicists to confront questions that are otherwise easy to avoid. Why does space-time have the properties it does? Why does it resist certain forms of manipulation more than others? Why does causality appear so deeply protected? These questions do not require faster-than-light travel to be useful. They are valuable precisely because the travel remains out of reach. Another reason this remains a beginning is that physics advances unevenly. Breakthroughs rarely arrive fully formed. They emerge through decades of partial insights, false starts, and reframings. What appears stagnant from the outside often represents slow, cumulative progress beneath the surface. The mathematics of space-time manipulation has grown more sophisticated. The understanding of vacuum energy has deepened. The dialogue between gravity and quantum theory has intensified. None of this produces headlines. All of it matters. There is also a cultural dimension. Science fiction has trained us to expect dramatic leaps, sudden inventions that transform civilization overnight. Real physics moves differently. It advances by tightening constraints, refining definitions, and clarifying what questions are meaningful. Warp-based, faster-than-light travel has already performed one of its most important functions. It has clarified what the speed of light actually limits. It does not limit how fast space can change. It limits how information propagates locally. That distinction alone reshaped modern cosmology and continues to shape theoretical work. This insight stands regardless of whether warp travel ever becomes possible. From this perspective, the true breakthrough may already have occurred, not in technology, but in understanding. The universe is not governed by simple ceilings. It is governed by relationships. Speed, energy, time, and geometry constrain one another in subtle ways that defy everyday intuition. Learning to think in those terms is itself a form of progress. As research continues, warp-based ideas may be absorbed into larger theories and lose their distinct identity. They may become special cases of more general principles, much as black holes evolved from curiosities into central features of astrophysics. Or they may remain permanently at the edge, permitted but unreachable, serving as reminders of the universe's depth. Either outcome would still justify their study, because the value of a scientific idea is not measured solely by what it enables, but by what it reveals. Warp-based faster-than-light travel reveals a universe that is flexible but guarded, imaginative but disciplined. It reveals laws that allow extraordinary possibilities while surrounding them with constraints that demand understanding rather than force. That balance is not accidental. It suggests that reality is not structured to reward haste, but to reward insight. And insight, unlike speed, compounds over time. Why this is still the beginning, not the breakthrough. At the edges of physics, progress often feels paradoxical. The more deeply a problem is explored, the less it resembles a problem waiting to be solved, and the more it resembles a mirror, reflecting the assumptions brought to it. Faster-than-light space-time manipulation has become such a mirror. What it reflects is not a path forward, but a pattern. Again and again, the equations allow just enough freedom to provoke imagination, and just enough resistance to prevent recklessness. Every apparent loophole reveals a deeper constraint. Every attempt to bypass a limit exposes another boundary, quietly enforced not by prohibition, but by instability, imbalance, or loss of coherence. This pattern suggests that the universe is not structured around simple rules like allowed and forbidden. It is structured around balance. Speed is balanced by causality. Geometry is balanced by energy. Freedom is balanced by consequence. Warp-based concepts sit precisely at the intersection of these balances. They are not anomalies. They are stress tests. Ways of asking how far the structure can bend before it stops making sense. From this perspective, the most important outcome of faster-than-light research is not whether it works, but what it reveals about the nature of physical law. It reveals that limits are rarely arbitrary. They emerge from deep interdependencies. The speed of light, for example, is not merely a maximum velocity. It is a conversion factor between space and time. It sets the scale at which causality, energy, and geometry remain coherent. Attempts to outrun it, directly or indirectly, inevitably disturb that coherence. Warp-based space-time manipulation does not ignore this. It engages with it. By trying to rearrange geometry rather than outrun signals, these ideas respect the letter of relativity while challenging its spirit. The resulting tension exposes where the theory is strong and where it is incomplete. This is why the discussion remains active. Not because physicists expect a sudden technological leap, but because the questions refuse to settle. They touch too many foundational issues: vacuum structure, quantum limits, temporal ordering, stability, to be dismissed as curiosities. Each partial answer spawns deeper questions. Why does negative energy exist at all if it is so tightly constrained? Why does space-time permit solutions that threaten causality only to surround them with apparent safeguards? Why does the universe allow extreme geometry in principle, but resist it in practice? These are not engineering puzzles. They are questions about why reality has the shape it does. In this sense, faster-than-light space-time manipulation occupies the same conceptual space once held by other transformative ideas. Before thermodynamics was formalized, perpetual motion machines exposed the necessity of entropy. Before quantum mechanics, atomic instability exposed the limits of classical physics. Those machines were never built. Their impossibility clarified deeper laws. Warp-based, faster-than-light travel may play a similar role. Whether it remains forever unattainable or becomes possible in some distant future, it already serves a purpose. It sharpens our understanding of why the universe behaves the way it does. There is also a quiet lesson here about ambition. Human history is marked by a desire to overcome distance, delay, and limitation. Each technological advance compresses the world a little more. Communication becomes faster, travel becomes easier, horizons recede. Physics suggests that this trajectory cannot be extrapolated indefinitely. At some scale, progress stops being about speed and becomes about comprehension. The universe does not yield its deepest structures to force or haste. It yields them to patience. Warp-based concepts tempt us with the idea that distance itself might be negotiable. Physics responds by reminding us that distance is not just a measurement. It is part of a larger structure that preserves order. Understanding that structure may be more valuable than bypassing it. This does not mean the future is static. It means the nature of advancement may change. Instead of crossing the universe quickly, we may learn to understand it deeply. Instead of shortcuts through space, we may find clarity about time, energy, and causality. Such clarity would be a different kind of breakthrough. It would reshape how we interpret cosmology, how we think about beginnings and endings, and how we situate ourselves within a universe that is both permissive and restrained. In that sense, faster-than-light space-time manipulation is not a destination. It is a boundary marker. It shows us where our current theories reach their limits and where new ideas are needed. Standing at that boundary is not failure. It is a necessary stage of understanding. The universe has always revealed itself this way, through questions that cannot yet be answered, but also cannot be ignored. As the discussion closes, one thing becomes clear. Whether or not faster-than-light travel ever becomes possible, the pursuit of the idea has already accomplished something profound. It has forced physics to confront its assumptions about space, time, and causality. It has revealed the elegance and restraint built into the structure of reality. And it has reminded us that the most important journeys are not always measured in distance. Some are measured in understanding. The universe does not promise us shortcuts. It offers us depth. And in that depth, there is still more to explore. Why this is still the beginning, not the breakthrough. By the time ideas reach the edge of physics, they tend to shed their original purpose. What began as a question about travel becomes something quieter and more enduring. A question about structure. Faster-than-light space-time manipulation has followed this path. It no longer stands primarily as a proposal for motion, but as a lens through which the universe reveals how carefully it is arranged. At this stage, it becomes clear that the most important outcome of this entire line of thought is not whether it leads to a device, a vehicle, or a method. It is what it teaches about restraint. The universe does not close the door on extreme possibilities. It leaves it slightly open, just enough to show what lies beyond, but surrounds the threshold with conditions so exacting that only understanding, not force, can approach it. This pattern appears again and again. Wherever the laws of physics allow something extraordinary, they also demand balance, coherence, and consequence. Warp-based, faster-than-light concepts sit precisely at that threshold. They are not forbidden. They are permitted under conditions that strain every known framework. They demand energies that challenge quantum theory, geometries that test general relativity, and causal structures that push against the foundations of time itself. Each demand is not arbitrary. Each seems tuned to preserve something deeper. That deeper thing is not speed. It is consistency. Space-time, as described by our best theories, is not optimized for traversal. It is optimized for order. Causality must hold locally. Energy must balance globally. Geometry must respond smoothly to stress. When any of these conditions are violated too aggressively, the structure reacts. Not with a rule, but with instability. This is why faster-than-light effects remain theoretical. Not because physics is incomplete in a trivial sense, but because physics may already be complete enough to signal caution. It is tempting to interpret this as a disappointment. But from another perspective, it is an achievement. The laws of nature do not merely describe what happens. They encode priorities. They protect coherence over convenience. They allow exploration, but resist shortcuts that would unravel the relationships that make prediction, memory, and meaning possible. Understanding this reshapes how progress itself is defined. If faster-than-light travel were easy, distance would lose significance. Events, separated by vast spans of space and time, would collapse into immediacy. Cause and effect would blur. History would lose its structure. The universe does not appear to be built for that. Instead, it appears built to allow separation, sequence, and development. Distance gives rise to diversity. Time gives rise to evolution. Limits give rise to structure. Warp-based space-time manipulation challenges those limits just enough to reveal why they exist. In doing so, it reframes humanity's place in the cosmos. We are not explorers in a universe waiting to be crossed. We are participants in a universe that unfolds slowly, governed by relationships that reward patience more than speed. This does not diminish curiosity. It refines it. Rather than asking how quickly we can reach the stars, physics invites a different question. What does it mean that the stars are so far apart? What does that distance preserve? What does it make possible? The answers point not toward frustration, but toward perspective. Even without faster-than-light travel, the universe is accessible in other ways. Through observation, we see back in time. Through theory, we connect distant phenomena under shared principles. Through understanding, we traverse conceptual distances that no spacecraft ever could. In this sense, the deepest form of exploration has already begun. The study of space-time manipulation reveals a universe that is neither hostile nor accommodating, but precise. It offers possibilities with one hand and constraints with the other. It invites inquiry, but demands humility. That balance is not accidental. It suggests that reality is not designed to be conquered, but to be understood. Faster-than-light ideas matter not because they promise escape from cosmic distance, but because they clarify the nature of that distance. They show that separation is not merely a challenge to overcome, but a feature that shapes coherence, causality, and meaning. The universe does not hide its secrets behind walls. It hides them behind depth, and depth takes time. If one day space-time engineering becomes possible, it will not arrive as a sudden triumph. It will arrive as the culmination of centuries of insight, earned slowly, cautiously, and with respect for the structure it engages. Until then, the value of these ideas lies exactly where they are now, at the boundary, where imagination meets mathematics, where possibility meets restraint, where speed gives way to understanding. This is not the end of the story. It is where the story finally becomes clear. Why this is still the beginning, not the breakthrough. As the discussion reaches its quiet end, a final shift in perspective becomes unavoidable. The question that opened this journey, whether faster-than-light travel is possible, no longer feels like the right question at all. It belongs to an earlier stage, when limits were treated as obstacles and distance as an inconvenience. What remains is a different inquiry, one that sits deeper than technology. Why does the universe allow us to imagine such possibilities, only to surround them with conditions so severe that they dissolve into theory rather than practice? This pattern is not unique to space-time manipulation. It appears wherever physics approaches its own foundations. At those boundaries, the universe seems to speak in a particular language, one that permits but does not encourage, that reveals but does not yield easily. Faster-than-light space-time concepts are written in that language. They show that the universe is not sealed shut. There are no absolute walls declaring never. Instead, there are gradients, steep, unforgiving gradients that rise sharply as one approaches them. Energy grows without bound. Stability fractures. Causality bends toward ambiguity. The lesson is subtle. The universe does not forbid shortcuts. It makes them expensive in ways that are not merely technical, but conceptual. To cross certain thresholds, one must pay not only with energy, but with understanding. And even then, the cost may be more than any civilization would be willing or wise to bear. This reframes the idea of progress. In the early days of physics, progress meant control. To understand something was to master it. To name a law was to bend nature to human intention. Faster-than-light travel fits naturally into that mindset. An ultimate act of mastery over distance. Modern physics tells a quieter story. Understanding does not always lead to control. Sometimes it leads to restraint. Sometimes the deepest insight is recognizing why something should not be easy, even if it is permitted. Warp-based space-time manipulation teaches exactly this. It reveals that the universe is not arranged to reward ambition alone. It rewards alignment. Alignment with structure, balance, and coherence. Technologies that ignore these qualities collapse under their own weight, long before they reshape reality. Seen this way, the speed of light is not an enemy to be defeated. It is a stabilizing feature of a universe that values order over immediacy. It ensures that events unfold in sequence, that causes precede effects, that histories remain intelligible. Attempts to bypass it, no matter how cleverly framed, brush against those deeper priorities. This does not diminish the wonder of the ideas themselves. On the contrary, it deepens it. That space-time can even be imagined as something that flows, bends, and carries regions of reality with it is extraordinary. That such ideas emerge naturally from equations written over a century ago is a testament to the depth of human insight. Einstein did not set out to describe warp bubbles or cosmic shortcuts. He set out to understand gravity. In doing so, he uncovered a universe far more flexible and far more disciplined than classical intuition allowed. Every generation since has inherited that flexibility along with its constraints. Theoretical physicists continue to explore these boundaries not because they expect to cross them tomorrow, but because boundaries define shape. They tell us what kind of universe this is, and this universe appears to be one where understanding outruns action. We can imagine more than we can build. We can calculate more than we can engineer. We can describe more than we can safely disturb. This imbalance is not a failure. It is a safeguard. It ensures that knowledge grows faster than power. From this vantage point, faster-than-light travel ceases to be a destination. It becomes a reference point, a way of measuring how mature our understanding truly is. Any civilization that could safely manipulate space-time on such scales would not merely be advanced. It would be deeply integrated into the logic of the universe it inhabits. Such a civilization would move carefully, if at all. Perhaps that is why the universe feels so quiet, not empty, but patient. It does not rush. It unfolds. Galaxies drift apart over billions of years. Stars live and die on timescales that dwarf civilizations. Light itself takes its time, carrying stories from distant epochs without urgency. In such a universe, the desire to arrive instantly feels slightly out of place. This does not make curiosity naive. It makes it human. We ask these questions because they test the edges of what we are allowed to know. They stretch imagination against structure. They reveal the difference between what is mathematically conceivable and what is physically meaningful. And that difference matters. Because meaning, in the end, is not found in how fast something happens, but in how coherently it fits into everything else. The universe has shown us that it can be bent, but not casually. That it can be connected, but not cheaply. That it can be understood, but not rushed. Faster than light space-time manipulation stands as a reminder of this balance. Not a promise of escape from cosmic distance, not a blueprint for machines, but a quiet lesson written into the geometry of reality. Some frontiers are meant to be crossed. Others are meant to be approached, studied, and respected. This one may be both. And for now, that is enough.